So these are by using this notion, we can now give conditions for measure preservation. And the first one is if we have a one Lipschitz map, which is uniformly differentiable modulo P, so for K1, then the map is measure preserving if it is balanced modulo Pk for some K which is not less than N1F. I recall that N1F, this one, it is the smallest K when we from which moment this equality, this congruence holds. So this is it must be balanced modulo Pk, and the rank of the Jacobi matrix of matrix consisting of partial derivatives must be M, this nth of maximum possible at all points. This is a sufficient condition. But when M is equal to N, these conditions become also necessary. The function is measure preserving if and only if F bijective modulo Pk for all K, which are greater than N1F, and the determinant of the Jacobi matrix must not be zero modulo P for all everywhere. And finally, the function. This is equivalence statement. This function, one Lipschitz function. The function means one Lipschitz method. Yes, right. The function is measure preserving if and only if it is bijective modulo Pk for any or for some. You can choose any one K, which is greater, not less than Nf plus 1. What does this mean? This means that you can check whether this function satisfying this condition, this function is measure preserving. So this means bijective modulo Pk for all K, just by checking whether it is bijective modulo Pk for some K, usually very small. For example, if N1F is 1 for some K, this is enough to check that it is bijective modulo P square. So the mapping of the residue ring modulo P square is bijective. I will I will prove this because this is the idea goes back to a classical result from which the periodic analysis emerged. This is a famous Hansel's lemma, which read that if a polynomial with integer coefficient has a root modulo P, and the derivative is not zero modulo P, then F has a root in a periodic integer in the root, and this root Y is congruent to x0 modulo P. This is famous Hansel's lemma. And actually, I will prove this theorem only for polynomials, just to give you an idea how these proofs are obtained. And the theorem read that a polynomial is measure preserving if and only if it is bijective modulo P, and its derivative is not zero modulo P for all x 1, 0, etc. P minus 1. So this is what I'm going to prove, and actually you will see that Hansel's lift, how it works, this Hansel's lift. First of all, we will prove sufficiency just by showing that these two conditions imply bijectivity modulo Pk for all K, and we will prove this by induction on K. This is the base of induction, right? The base, the function, according to our conditions, is bijective modulo P. So for K1, it is okay. Assuming F is bijective modulo Pk, prove that it is bijective modulo Pk plus 1. What we need to show? we need to show that given arbitrary number from here, well, arbitrary element of the residual ring modulo pk plus 1, there exists a unique x, a unique solution x of this congruence modulo pk plus 1. We can represent this this y as y tilde, where y tilde is from here, is from here, means from 0, 1, p, k minus 1. So this is what is stand in the lower order bit positions of y, plus pk. This is higher order digit of our y. So this is a unique representation. And by induction hypothesis, there exist, because if we take this modulo pk, we will get y tilde. There, by induction hypothesis, there exists a unique solution of this congruence modulo pk. Now we will show that then there exists a unique element of finite field of p elements. So a unique R from 0 to p minus 1, such that this congruence holds. This will be, of course, this will have the proof. We can do like this. We can, by using the uniform differentiability, we develop. See, we write like this. We write like this. So this is increment and multiplied by a derivative, right, at this point. But what is this? What is this? What is this? This is, we take f and apply and calculate the value of f at this point, but modulo pk plus 1. Because of this, this must be congruent to y modulo pk. Then it is of this form, and this is unique. So given x, this is unique. So we have this congruence. But now we just write that this one must be congruent to this one to prove this solution, right? To prove that this. So we must prove that there is a unique T which satisfy this congruence. But this is clear because this is, we cancel this, right? K here and k plus 1 here. So this is congruent. This is equivalent. This congruence is equivalent to this congruence modulo p, but this is not 0. This we know. This is given, and we need to find R. We need to find R. We need to find R, which satisfy this congruence. But this is not 0. So this we have a linear equation in a finite field. Of course, it has a unique solution. We just multiply both parts by the inverse element of this. I mean the multiplicative inverse. That's all. We are done. Is this clear? This is what called Hansel lift. Okay. No question. Okay.
Question? No, I guess this is clear.
Well, if it is okay, then I proceed. Okay, but now why I can now replace this by equivalence statement? The polynomial is measure preserving if and only if it is bijective modulo p square. Well, from our proof, it immediately follows that if it is bijective modulo p, and the derivative is not 0 modulo p everywhere, then it is bijective modulo pk for all cases. Then it is bijective modulo p square. But if it is bijective modulo p square because it is one Lifshitz, it is bijective modulo P. But if it were not, if it will be, it will be this will be zero at some point. At some point, then this solution cannot be modulo P square, cannot have a unique solution, either no solution, either every solution. That's all. So this is these are two equivalent statements. This is the idea. This is the idea in the proof. This is what is Hansel lifted. So we have proved this important theorem, which give us very practical instrument to determine measure preservation for functions which are uniformly differentiable modulo P. So the slightest smoothest condition, so to say. What about ergodicity? Means transitivity modulo pk for all k. For example, the following theorem holds: if we have a one Lifshitz ergodic function which maps Zpn to Zpn and which is uniformly differentiable modulo P, then necessarily n is 1. So multivariate smooth ergodic maps, smooth means uniformly differentiable modulo P, exist only in dimension 1. I will not give this the proof of this. I will only show you. So make a comment why it is so. What is the basic reason for this? Well, let it be transitive modulo pk. Then n is some n. Then if we iterate f that many times, we will have starting from this point, then we obtain this congruence modulo pk for all x by the transitivity, right? But if we take these two vectors and calculate this by using differentiability, we obtain this one. But what is this? You see, this is this mapping modulo, this is small mistake, not pk to the power n, but pk to the power n minus 1, to the power n minus 1, here could be. Because if we take pk fp here, only here pk minus 1, only here pk minus 1, this must because this must be modulo pk. Modulo pk. This must be this must be a fixed point. So this mapping of must be transitive. In order to this mapping is this mapping modulo. No. Okay. Because I start with pk plus 1. No. N is okay here. So this mapping must be this is an affine mapping. It must be transitive. It must be transitive as a mapping, as a mapping of. It must be transitive as a mapping, an affine mapping of a finite field. But this, the affine mapping are transitive in a very rare cases. Only when n is 1 or n 2, but then p is 2. This case also included can be excluded from. It can be shown that in our case, one Lifshitz map it's not possible, and this is a well-known result from linear algebra. For example, here you can find the proof. Well, it's well known. So this is why we can deal only when we speak of uniformly differentiable criterion for ergodicity of uniformly differentiable functions. Then necessarily n is we can speak only in dimension 1. And in this case we can state a number of and prove the number of theorem. I will not going to prove, and they can be proved well in a sort of Hansel lift. And what we need to show from which moment we can use this Hansel lift. We need to estimate this n to f. So the theorem which is well, so to say, well, more or less standard statement. If we have a one Lipschitz function which is uniformly differentiable modulo p square, not p1, p square, then f is ergodic if and only if it is transitive modulo pn for some n greater than this one, if p is odd, or that number if p is 2. This is the basic, so to say, theorem. And well, for special classes of function, like for example function a, it can be this can be estimated, and it shows that this you can calculate this number, and for C the functions, C functions or B functions, the ergodicity, to check ergodicity is very easy. One must just check transitivity modulo p square or modulo p cube, and that's all. The proofs are well lengthy. I am not going to prove, but from this it can be derived that we can obtain necessary and sufficient conditions in terms of coefficients. And for example, we can see that ergodicity for the case P2, the ergodicity of functions from the class B is guided only by 6 bits. Only by 6 bits. The other are just arbitrary. And the function, if you this way fix these bits in these coefficients, then the function is ergodic, and this is if and only if condition. These are more examples which, for example, people can try to prove themselves. This is actually an exercise by using that theorem which just I have proved. And now we check to ergodicity, to the ergodicity on balls. This is also an important special case where, for example, we need to study only the ergodicity, not on the whole space, but on some ball. We know that the one Lipschitz map is not ergodic on the whole space, but some ball is invariant with respect to action of this map, and we want to know whether it is whether the map acts ergodically on this ball. But it is easy. It is easy because if this ball is invariant, then we can consider this so to say this map and study the ergodicity. I just take and it is clear that the map F is ergodic on this ball because this ball is invariant if and only if this map of variable z is ergodic on the whole space. Later I will go with some examples. Well, very soon, I'd rather say. But the question about ergodicity of one Lipschitz function over periodic spheres, spheres is more complicated, because what is p-adic sphere? P-adic sphere of radius p to the minus k is the union of disjoint union of p minus 1 spheres of radius p to minus k minus 1. So the ergodic map on spheres, and this was a problem which stands well quite a long time. About ergodicity on spheres, I will. This also can be. I'll skip all these details because the proofs are getting more and more involved here. I only show that this is the theorem which says, which give necessary and sufficient condition for criterion of ergodicity of one Lipschitz maps belonging to the class B on spheres, on a sphere, and this is the criterion. Here we use the primitivity modulo p square. What means primitivity modulo? The derivative must be primitive modulo p square. Primitive element is the generator, the generator of the this group this group when p is odd, this group is cyclic, and we can so this is the derivative must not only not be zero, but it must be a primitive element. Okay, a modulo p square. There are and this way we can find a solution to a problem which was posed for at least 10 years by Gerlach, Renikoff, and Lindahl. The perturbed monomial map. This monomial map, where there's a small perturbation, small, periodically small, of this form. For example, originally it was stated for polynomials. It is ergodic on the spheres centered at 1, if and only if this map is a primitive modulo p square. So this is a complete solution of this problem, and it is done by the methods which I just have explained. These are some examples of functions which are transitive on, which are ergodic on spheres, You see that there are some exotic or less exotic functions. And now these works were developed significantly on different spaces. One, for example, Memich, Nassim and Memich did a lot in these directions after that. And now I finish with the ergodic theory. I skip for a moment this topic and jump to applications in order you not to forget what just have been said. So we are going to discuss how to apply the results of measure preservation ergodicity to some special areas. For example, we want to construct Latin square. What is Latin square? A Latin square is a square matrix. Which contains symbols, p-distinct symbols. P is not necessarily prime, arbitrary number, such that each row and each column of the matrix contains this symbol exactly once. So these are binary quasi-groups in some algebraic terminology. And any operation defined by Cayley table is a Latin square. So the operation must be invertible with respect to each variable, and this means that this always has a unit solution. But this operation need not be associative. So quasi-group is not necessarily a group. So the Latin square is a two-variant map. Of this sort. Such that which is invertible or bijective with respect to each variable. there is a huge need for Latin squares. So they used for games, Sudoku, serious applications, private communications, network, password distribution, coding theory, cryptography, etc. And there is not a problem to construct one small Latin square. This is a huge combinatorial theory how to do this, but for small cases, this is not a problem. The problem is to write a software which produces a number of largely Latin squares. But this is only a part of the problem. The second part of the problem that in constrained environments we cannot store the whole matrix. Store matrix, we just have no memory. No memory for this. So, but we need to calculate the every entries of the matrix which we need on the fly by a certain program, and this can be done by the use of our theory, which we just have learned. We will say that a one Lipschitz map. This is one Lipschitz map is a Latin square modular pk. If the reduced map modular pk, this is a Latin square. So this is a function. This is a function which is bijective with respect to each variable. How to construct a Latin square modular pk where k is large? This is an answer. We just follows from the criterion we just have proved. If we have one Lipschitz function which is uniformly differentiable modulo p, and this function, it is a Latin square modulo pk for all k, if and only if it is a Latin square modulo pn1f. This parameter which was known. And second condition, the partial derivative is not zero modulo p for it does not vanish modulo p. Each partial derivative, you have two partial derivatives. And the equivalent statement, if and only if f is bijective modulo p to the power n1f plus 1 with respect to either variable. That's all. This is an answer and immediate applications. It immediately follows from the theorem by measure preservation. I will not prove this. For example, this one. We take here arbitrary t functions, so arbitrary one Lipschitz function, two-adic functions on two variables. This is arbitrary two-adic number, or arbitrary integer, for example. This is a Latin square on two k symbols for every k. You can take k equal to 1024, for example. So this is a Latin square of dimension 2 to 1024 by 2 to 1024. And this is also a Latin square on 2 to the n symbols for every n. This follows directly from the problems, and we can calculate every entry on the fly immediately by using very restricted computers which is less not very powerful. So this is the proof. This is the proof. This is a Latin square modulo 2, and the derivative are 1 modulo 2. That's all. Well, the same idea holds if we want to construct a Latin square on on a composite numbers of symbols. For example, if this is a polynomial and this is, we can take this function. This is a Latin square for arbitrary n on that many symbols where k, l, r are arbitrary. This is the answer again. So I omit further discussion on this item. The idea is clear, I suppose. Mutually orthogonal Latin square. What are mutually orthogonal Latin squares? These are another things which also needed. well, a pair of Latin squares are said to be orthogonal. If when the squares are superimposed, we obtained a matrix of p square ordered pairs, and every pair appeared in the matrix exactly once. For example, this is a Latin square, this is a Latin square, and this is the Latin square of 3 by 3. If you impose this over this, you will obtain 0, 0, right? This will be 1, 1. This will, for example, 2, 0, right? So you see that all pairs are ordered, all pairs are different. So these are orthogonal Latin squares. Mutually orthogonal Latin squares, they are also used widely in experiment design, for example, to provide consistent testing of samples in cryptography in many cases. And we will need to create a software which can produce a huge number of mutually orthogonal Latin square, and which can done it some in a pseudo-random way, whatever it be. And again, we can solve this problem by using what we have just proved. So if we have a pair of uniformly one Lipschitz functions, which are uniformly differentiable modulo p. There are a number of that functions, you know, and let f and g be Latin square modulo pk for all k. We know how to construct Latin squares modulo pk for all k. Well, it's, by using these functions. This pair is a pair of mutually orthogonal Latin squares for all k, if and only if the following function preserves measure. That's clear, right? This is one. But the letter holds if and only if, that not only every this is not zero, every partial derivative is not zero, but the determinant is not zero modulo p. This is the answer. And we can again, this is a criterion of measure preservation, which we just have proved, and this is the answer for mutually orthogonal Latin squares. Okay. Again, we can construct a number of Latin square of these ideas, but not exactly for polynomials. I think that this is clear. Because it's just an immediate consequence of the criteria of measure preservation. But now about uniform distribution. Actually, the most applications are related to so to say, to constructions of pseudo-random sequence. Usual construction of pseudo-random sequence, if we take some x and start it, let's say the number, and start it iterated, for example, modulo p for large pn for large n, and if this sequence is uniformly distributed, we say that at least it looks like random. But what is it? And there is let's call direction in theoretical and practical directions how to construct uniformly distributed sequences. And there are a number of publications, and I will now show how these results, many of the results, can be proved immediately, which follows immediately from what just have proved. For example, this theorem, the length of the shortest periods of the sequence defined by the recursion, this one, this, we see this, the function, is 2 to the power n, if and only if A is 1 modulo 4 and B is 1 modulo 2. What is this inf? I jump here. This is generalized multiplicative inverse. What does this mean? You take a function, you take, well, here is a definition. Here is the definition. So you cut off leading zeros all leading zeros of the base period representation of X, then the obtained number, because is now invertible as a periodic integer, right? You take the inverse number and multiply it again by append again these leading zeros. That's all. Okay. Okay. So by using the criteria in terms of folklore criteria, which I stated last time, the following theorem can be proved. If P2 and F is ergodic, then both compositions are ergodic. Both compositions are ergodic, and vice versa. If either of compositions is ergodic, then F is ergodic. Look here, we have this composition. We have this composition with what? With what? Here is an affine map, and there is a criterion for ergodicity for an affine map. For P2 it reads, 1A must be 1 modulo 4, and B must not be 0. Modulo P means B must be 1 modulo 2 if P2. This exactly what is written here, right? So that's all. The result proved. And this way we can obtain a number of theorems by this sort. For example, all these functions ergodic, generalized inverse are all ergodic, etc., by using different criteria. This function, it is used in some string ciphers. It is transitive modulo 2k for all k. It also follows easily for ergodicity criterion for Wallenschup's functions. This function is uniformly differentiable modulo p square. This is the proof. And what is n? N to f is less than 3. So it is sufficient to show that the function is differentiable modulo 32. Is transitive modulo 32 to 2 to the power 5. Just directly calculate, take 31 iterations of 0 and see that it is transitive. That's all. Then it is transitive modulo to k for all k. Another generator, inversive generator. Well, function like this. This function is not every way defined, because not every way periodic integer has has an inverse. But this function has this ball is invariant under action of this function. We will use this. We will use this new function. Then we obtain this one, and our function is ergodic if and only if this function is a variable that is ergodic on the whole space. But we have ergodicity criterion, and this is a C function. Immediately apply the criterion of ergodicity of C function. We have this criterion in terms of coefficients. We immediately apply this criterion and immediately obtain the result. And another generator, that inversive generator of this form, same idea, a little bit more complicated function, but the same idea. And new inversive generators can be constructed, let's say, any you like. And one more example, for example, very popular in cryptography, exponential generators. Well, using the criterion or ergodicity of spheres, we can we can prove that this generator attains the longest possible period, means this length, if and only if it is ergodic on spheres. And actually, we use just immediately apply criterion of ergodicity on spheres. Well, that's all about the applications. And I return to the another theoretical issue of the theory, which is plots of automata maps in Euclidean space. This is an important thing which will be used in another application area in our application for physics intensively, but also to pseudo-random numbers as well. Well, what I will do in simple words, we have an automaton function, So we send to the automaton infinite words, left infinite words, and obtain in the output left infinite words. Let's cut them words. We'll take this word. I'll take first cut symbols. Corresponding output word. Take first cut symbols corresponding to the output word. Write 0 point this one, 0 point this one. This is a number between 0 and 1, right? And this is a number between 0 and 1. So this is a point in the unit square. Do this for all input, for all k, for all x, infinite words, obtain a number of points, an infinite number of points in a unit square. Obtain all these points, take the closure in the unit square closure with respect to real metric, and if it is a closed set, then it is necessarily measurable. Measurable. What is the measure? The measure will inform us how complicated is the mapping. It tells us, and this is the answer. Given a one Lipschitz map, the following alternative holds. The measure either 0 or 1, and nothing in between. This is a sample map when the measure is 0. Yes, this is looks like Sierpinski gasket, right? And this one is not absolutely interesting. This is the measure is 1, so it's completely. Actually, it tells more. These points are either no-way dense. These points, all these points, which points? These points are either no-way dense, and in this case we will obtain measure 0. Or everywhere dense, and in this case we obtain measure 1. You see that there is go to proof. I will not prove this because I append the proof to this for your convenience, for people who are interesting. I append the proof to this presentation, but it is lengthy. It will take at least one lecture. So for those who is going to go into details, so you can go to proof. Just I will send the updated presentation to organizers, and I hope they put it to the site. Main idea here, you know that there are everywhere dense sets which have measures arbitrarily close to 1. Despite they are point sets, I mean, despite they are no dense. So these are so-called fat counter sets. The main problem in the proof is to show that fat counter sets here are impossible. But this, and I stop about this because we are for those who want to go to proof. Well, the complete proof is at the end of this presentation. You can read it by yourself. So we will say for short that one Lipschitz map or an automaton is of measure 0 if the measure of this graph say this is a plot in a unit square, and of measure 1 if otherwise. So only two cases. Of course, if we want to construct good pseudo-random generators, for example, we must use maps of measure 1. How to construct one Lipschitz maps of measure 1? This is also related to transitivity properties of automata. Well, I skip these definitions because actually this easier to explain on pictures. What is word transitivity? Given finite words of the same length, we say that automaton is word transitive if we apply to this word sufficiently number of times we obtain this word. So every word can be mapped to every word by applying the automaton sufficient number of times. This is word transitivity. This is just ergodicity, right? Because of our theorems, this is just ergodicity of automaton function. But there are other things which are not that directly related to ergodicity. Complete transitivity. We have given two finite words, this one and this one, of equal length. There exists a finite word such that if we input this word first, then we output, we have a word which ends with this one. This is a sort of butterfly effect, which is known from Jurassic Park. Yes, you know, well, Bradbury. Well, when one change of very short word completely change output. Change of this, we will obtain anything here we like. This is complete transitivity. And then absolute transitivity. This is stronger than complete transitivity even. We have three words, x, w, and w prime, such that these are equal. We send input word x, then there exists word y, such that we put the word w here and obtain as output the word which ends with w prime. This is absolute transitivity. A very strong condition, and this is the theorem. An automaton is completely transitive if and only if its measure is 1. So automaton which performs butterfly effect. So this is when the future strongly depends on the past. Loosely speaking. This is complete transitive. And but if an automaton is finite, so the number of states is finite, then the automaton is necessarily of measure 0. This is I also append the proof. It is shorter, but it is still too long to be exposed here. So for people who want go into details, please do this. So I have roughly 6 minutes, I see. So I'm finishing. So these are different conditions for complete transitivity, which can be also obtained. Well, this is one of them. The function if differentiable in some neighborhood, one Lipschitz function, and the second derivative is not zero. This condition holds, then this is completely transitive. For example, the following functions, t functions means p equal to 2. They are completely transitive. And for example, these functions, which are cryptographic functions, which are used in, these are the names of the ciphers, stream ciphers, which use these t functions. And the criterion, well, not the criterion, but sufficient condition of absolutely transitive. Absolute transitive. So if a derivative has 2 times differentiable function, 2 times differentiable, and the derivative have not more than a finite number of zeros in n0, then it is absolutely transitive. For example, for a polynomial, it is so. For a polynomial, if f a polynomial, then it is absolutely transitive. These are immediate consequences. So the following properties are ergodic or non-ergodic, and to be a measure 1 of measure 0, they are independent. These are examples. These are examples. This is that these functions, these 2 properties are independent. And then a constant function is never ergodic, but it can be either of measure 0 or of measure 1. It is also if a constant function represents a random sequence, then it is of course of measure 1. If it has some deficiencies in randomness, it may be of measure 0. And the same can be done. The same theory can be developed for iterations of functions in a similar way. In this way, we also have the 0-1 law. It also holds, but what we have here a strong theorem by Emil Lerner. If f is a polynomial of degree greater than 2, then NF, it has measure 1 in all dimensions. You see, here is dimension, the number of iterations in all dimensions. This means that actually, if we have a polynomial and iterated sufficiently long time and look only on the picture we obtain at the unit square, we cannot determine it. We have no chance, so to say, to determine it whether it is random or not. This is very loosely speaking, but I will use this property later in when consider physical applications. This is the strongest theorem. If f is a polynomial and degree greater than 2, then the distribution of points in the unit hypercube, any unit hypercube of any dimensions, tends to uniform as k, the number of iterations goes to infinity. This is what we know for today, and this is a strong result. Now we are coming to another very interesting point, that we can construct all these polynomials, all these functions which distributions tend to uniform, but we can note anyway that the pronouns straight lines may still occur in the plots. If I have here, no, I should run. Oh, the time is over. My time is over. Then I will finish here, because now despite I have a couple of minutes, we will, in the next lecture, we will step by step go to physics, and we will start from this moment. We will study functions which correspond to one Lipschitz functions, but these functions will be here. There will be functions defined on characters, on complex characters, and this will say a lot about all this behavior of our automata. So this is where we will stop. Well, see you tomorrow. If there are no questions or comments, well, then the lecture is finished.
Thank you very much, Professor Anashin. So, are there any questions, comments? So, not in the chat either. So let's thank again, Professor.
Okay, thank you.
So, thank you very much. We have a pause of 1 hour. Oh, 30 minutes. 30 minutes.
Yo lo presento a ver si me ven. Can you hear me, Christopher? Can you hear me?
I can hear you. Can you hear me?
Oh, hello.
Good morning.
Guys.
So we are about to start. So we have now Professor Chris Sider talking about periodic electrostatics. Thank you very much.
Thank you. Can everybody hear me out there okay?
That's okay.
All right, thank you. So first of all, I want to say that the notes that I've developed for this course are available online. They are web pages right now. You can go to, I'm going to put this in the chat, but it's cdsinclair.us. If you can't see the chat, I'll share my screen here in a second and get you that information. But hopefully that will allow you to follow along in case things are too small to see on the screen. So I'm going to go ahead and share my screen now.
Chris, can you hear me? Could you please send me the link to put it in the web page of the conference?
Of course, of course. Yes.
Thank you.
All right. So let me just start here. So first, I want to thank the organizing committee and the scientific committee for this conference. I know it's been a tremendous amount of work, especially because of COVID and everything that's happened since the conference was first scheduled. So I really appreciate the hard work. I really wish that I could be there. I apologize. I had issues with my passport. What I want to talk about today, well, today and tomorrow, is non-Archimedean electrostatics. So we're going to go through, we're going to start from a fairly basic place because I want to develop the theory. And also it's a summer school. I feel like I have a little bit more time to walk through some of the details. So I'm going to go over just a very quick introduction to the basics of probability, kind of how probabilists think about the world, or how I think about the world at least. I'm going to talk, there's a section on p-adics and related concepts. There's another course where you're learning the basics of the p-adics. That will be just kind of a quick overview, probably by this point, with what you've seen. Then I want to talk about an introduction to Boltzmann statistics. So these are a certain physical model for how particle systems and other thermodynamic systems behave. We'll be concentrating on particle systems. And then finally, I'm going to dive into p-adic electrostatics, kind of the subject of the series of lectures. The lectures are based on the following paper, and this was based on some work that I'd done previously and talked about a little bit at Santander and at p-adics 2021. So some of this will be a little bit of a review, but this is an opportunity for us to go a little bit deeper. I'm looking here at the bibliography because I want to say I'm obviously not the only person working on problems in this area. And there's a lot of really interesting research from a bunch of different directions on p-adic electrostatics and log gases and Coulomb models. All of these are kind of related concepts. And I just want to point to a couple of papers that will give you, a complementary perspective to what I'm going to talk about today. So one is this paper by Zuniga Galindo, Zebrano Luna, and Leon Cardinal.
Sorry. Can you please increase the font because we cannot see?
Okay, let me see. Maybe I can.
Okay, that's good. Thank you very much.
So oops, let me see. The papers I'm talking about, I'm gonna, well, this paper, the papers that I really want to refer to are graphs, local zeta functions, log Coulomb gases, and phase transitions. And then there's another paper by Zuniga and Torba on non-Archimedean Coulomb gas. And I I hope everybody goes out and reads those papers. They're very interesting. One of my students also, Joe Webster, talked about log Coulomb gas and some other related results. So again, a lot of people have worked on this, but I want you to know that there are other places to start this journey. All right, so I will increase the font here. So I was a little bit nervous about preparing this series of lectures, just because, you know, I don't know, talking to experts in the field is hard work. But what I decided to do is I wanted to go through just a little bit of basics of probability first. Now, this is going to be a review for a whole lot of people. If that is you, I encourage you to you know, listen with the back of your brain, but maybe check your emails or something. But this is just to kind of develop our intuition and thinking about ultimately some ideas that we're going to apply to mathematical statistical physics. So I'm not going to be able to go through all of these details, but they are here for people to read. All right. So I want to start very generally, and this is just talking about what we mean by sample spaces, events, and sigma algebras. So we envision a situation where we have some sort of experiment, a random experiment perhaps, or an experiment that's not random, but for which we don't have the information to necessarily predict what it's going to do. And we imagine that this experiment has some sort of collection of outcomes, right? Possibilities for what the experiment could yield. And we call the set of outcomes the sample space, right? Subsets of the sample space are called events, right? And we can talk about whether or not an event occurred, and that's whether or not we saw an outcome that was in the subset that we are considering. We're going to talk in a little bit about probability measures, but for now, a probability is just a number between 0 and 1 that allows us to say how likely an event E is going to happen. And we say P of E is the probability that E occurred. So in real life, oftentimes when we're doing this sort of observation, there might be a complicated experiment. Think of something in a laboratory with, I don't know, beakers and whatnot. And the set of outcomes of that experiment might be a very large space that's very difficult to describe. Often what we're doing instead is not trying to describe complete outcomes of the experiment, but we're taking a measurement. Perhaps we're measuring temperature, or maybe we're measuring pressure in our physical system, but we're doing a measurement. And in this context, a measurement in probability is something that we call a random variable, right? Of course, we might be taking multiple measurements at once. Maybe we're measuring the pressure and the temperature and some other things, in which case, instead of a random variable, we call it a random vector. And a random vector is just a vector of random variables. So if we have one of these random variables, one of these measurements, what are things that we might care about, right? What is the thing that we might care about from a measurement? Well, I think that the most obvious thing, if we think maybe temperature is the measurement that we're thinking about, just for an example, is what is the probability that the temperature falls into some region, right? What is the probability that the temperature is between 99 Celsius and 100 Celsius, right? That is a reasonable thing that we would want to ascribe probabilities to. And events of this sort, right, if I have A, B, I write the set X between A and B. That just means that is the set of outcomes that correspond to the random variable taking a value between A and B. All right, and obviously there's nothing special about the open interval here. We can do closed intervals, half closed intervals, other sets as well. Now, in probability, this is a concept that arises in analysis as well, is the idea of a sigma algebra. In probability, sigma algebras, they have a different kind of importance than in analysis. And so I want to talk a little bit about them and develop a little intuition there. But the idea here is that we have a bunch of events that we care about. Maybe these are, you know, talking about measurements of a random variable, but we have a number of events that we care about. And what we would like to do is assign probabilities to these events in some consistent way, right? Well, it turns out that for kind of complicated, and from my point of view, I think these reasons are a little bit boring. Oftentimes, you can't assign probabilities to every subset of a sample space. This is something that you've probably seen in analysis. There are issues. And so oftentimes we have to restrict ourselves to a smaller collection of events than just every possible subset in the sample space. And so in order to kind of axiomatize that, we might ask the question, what are reasonable things that we would expect these events and probabilities, how should they interact? What is a natural way of axiomatizing this? Right. Sorry, my dogs are making noise. Apologies. So one thing to say is that if there is an event and we can assign a probability to it, we are basically saying the probability that this event occurs is this number. And therefore, we should be able to also determine the probability that the event did not occur, right? That's going to be the complement, and that's basically going to be 1 minus that probability. So that seems reasonable. If we have events that we care about, we can assign probabilities to their complements, right? Another thing that we might want is that suppose we have a bunch of events, E1, E2. I'm thinking of these as a countable list right here. And suppose that we can assign probabilities to each one of those. So I have some notion of the probability that E1 occurred, some notion of the probability that E2 occurred, etc. Well, it seems reasonable in a full theory of probability that we would also want to be able, if we have that information, to assign probabilities to the event all of the E's occurred, right? Or none of the E's occurred, right? At least one of the E's has occurred, right? It seems like if we can assign probabilities to the events themselves, then we should be able to assign probabilities to essentially their unions and intersections. And so this leads us to the definition of a sigma algebra. And a sigma algebra is a collection of subsets of omega. We're calling those events, right? Satisfying these three properties. First, all of omega, the entire sample space, is an event that we can care about. Okay, that's great. That basically just says that we have all of the possible outcomes from our random experiment considered. Secondly, is if E is in the sigma algebra, then the complement is in the sigma algebra. And finally, if we do have a countable collection, countable or finite, but I'll just say countable collection in the sigma algebra, then the union of those things is also in the sigma algebra. It turns out that you can get the intersection of the EIs as well, or the ENs, for free, because basically once you have unions and you have complements, then De Morgan's laws gives us intersections as well. So we could write down a fourth bullet if we wanted to, that says if we have a countable collection of events, then their intersection is also an event in our sigma algebra. But strictly speaking, it's not necessary because we can just conclude it from De Morgan's laws. All right, so every sample space has at least one sigma algebra. There's the trivial sigma algebra. That's the empty set together with omega. It's easy to verify that that satisfies all of the axioms. It's not a very interesting sigma algebra, but it is a sigma algebra. If I pick my favorite event in omega, just one, right? If I look at the empty set, I look at that event E, I look at its complement, and I look at all of omega, that's a sigma algebra. Again, fairly simple sigma algebra, but a sigma algebra nonetheless. Generally, sigma algebras are much larger than these two examples I've given you. Generally, they have tons of sets in them. And so, for instance, it's also trivial to verify that the power set, the set of all subsets of omega, is a sigma algebra as well. And it's the biggest sigma algebra omega can have. All right. And so how do I want to say this? Analysts and probabilists both use sigma algebras because they're extremely important to develop the notion of probability or measure theory, right? And so what we want to to do is kind of talk about how do these two groups of mathematicians think about sigma algebras? Now, of course, I can't answer that completely because I'm only one mathematician. However, generally speaking, a probabilist sees the sigma algebra as something as holding information about the random experiment that we have the possibility of discerning, right? We have the possibility of observing or seeing, right? We think of it as a body of information. And this information consists of the events and their intersections and their unions, right? And oftentimes we use different sigma algebras to talk about different aspects of a problem because those sigma algebras encode perhaps different information about the problem that we're talking about. Analysts, at least the way I was trained in analysis, sigma algebras are necessary to develop measure theory. They're obviously extremely important, but they're just kind of a mechanism by which we can ensure that our definitions work correctly. They seem to be a little bit less central to the theory, at least the way we think about the theory. Certainly they're necessary for developing integration, but they take more of a background role. So it turns out that this next definition, well, this exercise, but it's easy to show, is that if we have a collection of sigma algebras, maybe just two, F1 and F2, or maybe some just infinite collection of sigma algebras, you can make a new sigma algebra by intersecting all of them, right? And this is this is sometimes called the sigma algebra generated by all those other sigma algebras, right? More generally, if I'm given some collection of sets that I care about, that I want to be events, right, then I can define a sigma algebra which contains all of those events. And basically what do I do is I look at every single sigma algebra that contains the events that I care about, and I intersect over all of those sigma algebras. That gives me a new sigma algebra, and it is the smallest sigma algebra that contains all of those events that I cared about. All right. Now, it is often the case, this is something that I'm sure you've run into, that your sample space is equipped already with some special sets that you think should be events, right? So for instance, if you have a topology on your space, right? Maybe your space is R or Rn, or even something more complicated, but it's topologized, right? Then a topology is a collection of sets that we call open, and we can look at the sigma algebra generated by those sets in the topology. Right? This is generally called the Borel sigma algebra, at least for most standard topologies, but this is the sigma algebra generated by the topology. We're gonna denote this, especially for R and Rn, and other sets as well. This script B is basically going to be the sigma algebra, the smallest sigma algebra that contains every single open set. All right, so every open set is measurable, or is as an event. Every closed set is an event, right? And a bunch of other things are events as well, but anything in the topology of R or Rn is going to be an event. Right. Now, we can also generate sigma algebras from random variables, right? So again, if we think about sigma algebras as holding information that we are able to discern, then the sigma algebra generated by a random variable is going to consist of the information that the random variable can discern. So, for instance, if I call my random variable x, I'm going to assume that it's a real valued random variable, right? So that the measurements that we're taking are real numbers. Then I can look at all of my Borel sets, right? Basically, think of these as being open sets and things that you can make from open sets. And I look at the inverse image of all of these, right? These form sets in omega. This is the set of outcomes for which, when you hit that outcome with X, you land in B, right? And if we use all of those events right there, right? We can generate a sigma algebra there, and that's called the sigma algebra generated by the random variable x. And again, it only contains information about the random variable x. So for instance, if you have a complicated sample space and maybe you have pressure measurements and temperature measurements, right? This sigma algebra has information that will allow you to discern differences in temperatures between outcomes. But this sigma algebra does not have information that will allow you to discern pressure differences between outcomes, unless for some reason the pressure was dependent on the temperature. And in this example, we're pretending that it's not the case. More generally, if I have a bunch of random variables, I can form the sigma algebra for which all of the events x inverse of b for all of the x's in my collection land in the sigma algebra. And again, sigma algebras are huge. Generally, we don't really talk about what a generic set in a sigma algebra looks like. I mean, there are theorems out there. You can go to Riemann and read some things, but generally these things are quite complicated. And oftentimes what we do is we really focus on the events that we care about and say, these are the events that we want to ascribe probabilities to. And all of the other probabilities that get assigned to the other events in the sigma algebra can be found from those probabilities, right, in some way. So even though these sigma algebras are often large, oftentimes we're still only considering probabilities really on a much smaller collection of events. This is just the world where we can ascribe probabilities, right? So we have the ability maybe to ascribe probabilities to events that we would never care about in real life. Yeah, great. Okay. I do want to talk just very briefly about product sigma algebras, right? So if you have two spaces, right? So if I have a space E, I'm calling it, and it comes equipped with a sigma algebra script E, some collection of subsets. And if I have another set F, it comes equipped with some collection of subsets script F. It's sigma algebra. Then what we would like to do is develop a sigma algebra on the Cartesian product of E and F. And basically what we do is we take all events in script E, and we take all events in script F, right? And then we form the Cartesian product of those events. These things are called rectangles. Sometimes they're called measurable rectangles. But if you can imagine, if E and F were the real axis, then and the sets that we took were just little intervals, then this set that we formed would legitimately look like a rectangle. There's more generic things out there than just things that look like rectangles, but we call them rectangles anyways. But at any rate, we can talk about the smallest sigma algebra on E cross F that contains all of the rectangles, right? And that is called the product sigma algebra. And we denote it, well, it's bigger than just the Cartesian product of the two sigma algebras. There are new events that are not formed purely from rectangles. So we can't really use the Cartesian product symbol for sigma algebras. So instead we use the O time symbol. It's just notation. And more generally, we can do this for any collection of events, right? For any collection of sigma algebras. Basically, any collection of sigma algebras, I can pick, from a finite number of those sigma algebras, some measurable sets. I can form some sort of measurable rectangle or parallelepiped. And then I can look at the smallest sigma algebra that contains all of those parallelepipeds. And then that will be the sigma algebra on the Cartesian product of all of our sigma algebras En. All right, we will be talking about sigma algebras a lot, and we will be seeing examples of them. This is just background material. Okay, so probability, again, probably review for most people, but nonetheless, a probability measure is if I have a sample space omega, and if I have a sigma algebra, a collection of events that I care about, Then a probability measure is a function that goes from the set of events that I care about, that sigma algebra, into 0, 1, right? So the value 0, 1, satisfying the following axioms. The first, the probability of the empty set is 0. This basically says that when you run the experiment, you get an outcome, right? You can't run the experiment and then nothing happened. So the probability of the empty set is 0. If I have a countable collection of disjoint sets, disjoint events, then the probability of the union of that thing should be the sum of the probabilities. This should somehow jive with our expectation, right? If I somehow say, well, what I care about is the probability that something happens in this event or something happens in this event, right? Well, somehow if those events don't overlap, it's sensible to think that the probabilities would add, right? Finally, if I have my favorite event in my sigma algebra H, and I want to compute the probability of the complement, then that's just 1 minus the probability. So in particular, that means the probability of all of omega equals 1. And then this triple, right, this collection where I have a set of outcomes, omega, I have a collection of events that I care about, script H, and I have a probability measure, P. This is called a probability space. Now, I want to back up just a little bit because a lot of the notions of what we talked about here extend slightly. Probability measures are measures, and so there's a more general notion, but it's largely the same. If I have a measurable space, which is a collection of a set E and a sigma algebra on that set, then a function mu that goes from the collection E into 0, infinity is a measure if the following two things are satisfied. Well, the measure of the empty set is still 0. And then if we have a disjoint countable union, the measure of the countable union is the sum of the measures of the sets in the union, right? For disjoint sets. So the only thing that really is missing there is essentially you don't get that the probability or the measure of the entire space equals 1, right? The measure of E could be quite large, and you don't have the ability necessarily to find the measure of complements or generic complements in general. The idea behind a measure is it's a way of ascribing size to sets. Well, for a probability measure, we think of probability as kind of being a size of that set, right? How often we see it can be thought of as a way of thinking about size. And in general, if I have a triple E, script E, and mu, it's called a measure space. Like a probability space, except just with a regular measure instead of a probability measure. A particularly important measure, one that you have seen before, whether or not you know it, is called Lebesgue measure. And Lebesgue measure is the unique measure, I'm calling it lambda for Lebesgue, on the Borel subset, which assigns to intervals just their regular length. Right? So if I have an interval AB, I don't care if it's open, closed, half open, half closed. If I have an interval AB, then the Lebesgue measure of that set is the length of the interval, B minus A. And from the axioms of measures, if I have a disjoint union of a bunch of intervals, right, well, then the measure of that set is going to be the sum of the lengths of those intervals that are in my disjoint union. So this is a relatively easy measure to work with, especially because even though the Borel sigma algebra is huge and has very complicated events in it, most of the events that we care about usually are just events along the lines of an open interval, or maybe not open, but an interval or some union of intervals, right? The kinds of things that we as human beings would care about are a much smaller set of things than in the Borel sigma algebra. And for the things that humans care about, in general, the Lebesgue measure is not too hard to compute. There are obviously exceptions out there, but for things that we're used to seeing. All right. Now, there's one other thing that we can do. Well, there's lots of other things that we can do, but one thing that is useful is that if you start with some big measure space, right, and then you pick your favorite subset, your favorite event in there, right, you can make a measure space on that event essentially by saying, well, I'm just going to look at all of the things in the original sigma algebra which intersect my set. That will give me a sigma algebra on my smaller set. And then I can use the same measure that I had before to ascribe probabilities or sizes, depending on if it's a probability measure, to those things in that sigma algebra. Right, so this is sometimes called the trace. It's kind of a way of projecting a measure down onto a smaller set. Right, projection maybe is the wrong word there. All right, and in fact, if we started with a probability measure, right, I could make a probability measure on my smaller set too, but I would have to make sure that I renormalize by the measure of the set. This denominator right here makes the resulting measure on the set A, equipped with its smaller sigma algebra, a probability measure. All right. Hopefully I'm not going too fast nor too slow. I know that this is probably information a lot of people know, but I really, I don't know. I kind of think of talks like this as we're going on a hike, right? And we're looking at things as we go on this hike, and we're kind of starting at the beginning. So if you've done this beginning part of the hike before, I apologize, but it's still a pretty hike. And we will get to some new places when we get closer to the top of the mountain. Okay, so we talked about measure space. A measure space is a space which is a set, a collection of subsets, a sigma algebra, and a measure. Well, if we don't have the measure and we just have a set and its sigma algebra, then we have what is called a measurable space because we can put a measure on it, right? So if we're given two measurable spaces, E script E, F script F, and a function from E to F, right? We say this function is measurable if for everything in the image sigma algebra, the pre-image is in the domain sigma algebra E. Right? So this is the notion of measurability. It's just saying that the inverse images of measurable sets over here are measurable over here, right? When you do the function. So the word measurable function, that's usually kind of the analysis term, the analysis word for it. The word for it in probability is random variable. So we talked about random variables at the beginning as being kind of measurements of a random experiment. Well, here I want them to be measurable, right? That is, I want to be able to assign probabilities to the set where the random variable takes a particular value. Right, so if I say measurable function or if I say random variable, those are really the same thing. It's just sometimes we think about them slightly differently, or maybe probabilists think about them slightly different than analysts, but from the viewpoint of definitions, they're the same thing. More generally, we can have random variables that are not real valued, right? And we are going to talk about this because before too long, we're going to have some p-adic valued random variables. Right, but if I have a random variable that's taking values in some other set besides R, right? Well, assuming that thing is a measurable space, right? Then we call X an E-valued random variable if the pre-image of every set here is in the sigma algebra for our omega. Right? Okay. Most of the time, we will be dealing with real valued random variables. At least for this part, we will get to p-adic valued random variables a little bit later. But for real valued random variables, we can do a decomposition so that we can write a real valued random variable x in terms of its positive part, x plus, and its negative part, x minus. And it doesn't really matter if you use non-negative or positive or non-positive and negative, right? The places where it equals 0 don't really come into the equation for what we're about to do. We're going to denote non-negative real valued random variables that are measurable with respect to script h as script h plus. Okay. This can be slightly confusing notation because on one hand we kind of think of script h as being a sigma algebra, and I'm decorating it with a plus, and I'm calling it a set of functions. But it turns out there's a way that the sigma algebra and the functions are equivalent, and so this is somewhat standard notation. Now, there's some special kinds of random variables. If anybody's taken probability before, you know names like discrete random variables, continuous random variables. There are special kinds of random variables. One special kind is when the set of values the random variable takes is finite. This is called a simple random variable. Or accordingly, if we're not using the random variable language, we call it a simple measurable function. Now, if the set of values is discrete, maybe not necessarily finite, but discrete, then we say x is a discrete random variable. We'll talk about continuous random variables in just a little bit. But for now, these are two kinds of random variables where we can just look at the range of the random variable and determine whether or not it is simple or discrete. Now, the very simplest simple random variables are called indicator random variables. And this basically says if you take a set A in your sigma algebra, then the indicator is the function that's going to take in an omega and spit out the value 1 if omega is in A, and spit out the value 0 otherwise. Sometimes in analysis, these are called characteristic functions. Not a big fan of that just because characteristic comes up in so many other places in math. So in general, I call them indicator random variables. And it turns out that every simple random variable can be written as a sum over some values an times the indicator on some set an. And that set is basically just the set of values, right? So the set of omegas for which an is the value when you plug it into x. So when you look at this thing right here, just think about what would happen. Clearly, if these ANs are different numbers, then the capital ANs are disjoint. So if I look at x of omega, right? Well, omega can be in at most of the 1 ANs. And if it is, it's going to return the value lowercase an, which is what we expect. Right, so this is just kind of a canonical decomposition of a simple random variable. And except for relabeling what you're calling the lowercase a's and the uppercase a's, this is a uniquely determined, right? So in particular, if you were to order your lowercase a's, then this would be completely determined. If you have a random variable that's taking values in an ordered set. Okay. Now, given any positive random variable x, this exercise is asking you to produce an increasing sequence of simple random variables xn such that the pointwise limits of this increasing sequence equals x. Right? This is basically saying that, I mean, think of a situation, let's think about Riemann integration for just a little bit. We will be talking about integration here in a second. But if you think about the Riemann sums, these functions that you make when you make Riemann sums, well, if you made the lower Riemann sum for a continuous function, right, that is going to be a simple function, right? It's going to take a finite number of values depending on how many intervals you broke the domain up into. Right? So, and if the lower Riemann sum will always be less than or equal to the original function, right? And if you take more and more or smaller and smaller sets on the real axis, right, you get better and better approximations. And so you get a sequence of simple functions which increases to this function right here. Now, this is obviously slightly more complicated than I made it out to be. In the situation where the random variable is continuous, then what I said works. In general, you have to be slightly more careful. But there is a way of approximating random variables by simple random variables, an increasing number. Hey, sorry, my dogs are barking. Hey, all right. Okay. So, and this is a useful observation from the following definition, something called a monotone class. We're not going to use this a lot here, except to say this is an extremely important idea in probability. So it's a good thing to see and to know about, even if we don't use it a whole lot in this class. Okay, so if I have a collection of positive random variables, this is called a positive monotone class if the following things are true. First, the function which is identically 1 is in the monotone class. Gonna have to kick these dogs out here in a second. Secondly, if I have 2 random variables in the monotone class, and I have 2 positive numbers or non-negative numbers, right, then the linear combination ax plus by is in the monotone class. Great, closed under linear or linear with positive coefficients. And finally, if I have a collection of random variables, a countable collection of random variables, a sequence of random variables, and this sequence of random variables is increasing to my favorite random variable x, then my favorite random variable x is also in the monotone class. That's the monotone part of the monotone class. So these things are closed under positive linear combinations and increasing limits, basically. Okay. And then the theorem says, the theorem is that if you pick any any event in the sigma algebra, and if the indicator random variable for that is in the set M, right, then it turns out that M, this monotone class, is all of the positive random variables. Right? So what this means is this gives us another way of characterizing random variables and or measurable functions. We originally said, okay, a random variable or measurable function is that if the preimage of any measurable set is measurable. Right? And that's a useful definition. That's great. What this is saying is that a measurable function can always be thought of as an increasing limit of simple functions, right? That basically these indicator functions that we put in, after we have indicator functions, we have positive linear combinations of indicator functions. Those are simple functions. And then the last property says that if we have an increasing limit of simple functions, if that converges to something, then that thing must be in the monotone class. All right. So this is very useful because it gives us a very concrete way of thinking about measurable functions by just saying, oh, well, they're limits of things of which I really do understand, right? Finite linear combinations of indicator random variables. How hard can that be, right? All right, so that theorem is an example of something called the monotone class theorem. There's a bunch of different variations of the monotone class theorem. So when somebody says they're using monotone class, you might have to ask which one. But they're all kind of this idea that you have this monotone class and you can draw conclusions about things that are in it based on looking at based on just checking that a very few things are in it at the beginning, the indicator functions. All right. Okay. Another important thing, we will use this just a little bit, but it is also important. If I have a subset of my sigma algebra that is closed under intersections, right, then this is called a pi system. Right? Some people call this a P system. This is basically Dinkin was responsible for this. If you've heard of the pi lambda theorem, this is the same pi in the pi lambda theorem. And basically another version of the monotone class theorem, or some people call this the pi lambda theorem, but is that if I have a set E, which is a pi system, so closed under intersection, that's it, that's easy. And suppose that thing generates my entire sigma algebra, right? Then if I have a monotone class containing the indicator random variables for all events in the pi system, right, then the monotone class equals the set of positive random variables. This is huge. And the reason that this is huge is because pi systems in general are much smaller than the sigma algebra that they generate. Let me give you an example. I told you that the Borel sigma algebra on R consists of, well, is generated by all sets in the Borel topology. So all open sets. Whew. All open sets. That's kind of a complicated thing to describe and talk about. That's a lot of work, right? But it turns out that there is a pi system which generates the Borel sigma algebra. And that pi system is just the set of open intervals, not open sets, right? Open sets are complicated. Open intervals are our friends. So what this says is that if you can check that your monotone class contains the indicators just for the open intervals, then you can be assured that the monotone class contains all of the positive measurable functions. And in general, it's much easier to work with an open interval than a generic open set, which is a countable union of open intervals. All right. So oftentimes, the monotone class theorem, or again, some people call it the pi lambda theorem, is useful because it allows you to check conditions on a sigma algebra, or perhaps a measure, based on a much smaller set of events then a priori you would have to check, right? A priori you would have to look at everything in the sigma algebra. This says that you can look at everything in a much smaller set, the pi system. All right. So that's a useful fact. We'll use that just a little bit, but it is something that I would like people to know. All right, expectations and integrals. Right? These are the same thing. So all of y'all out there know integrals. And so therefore you secretly know expectations, even if you don't know them for real. If you do know them for real, then this will be review. But we start with a simple random variable. And remember, a simple random variable, this can be positive here. The simple random variable can be given as a positive linear combination of indicator random variables. Right? This is just kind of like a step function or a generalization of a step function. Well, then the expectation of the random variable is given by you sum over the values of the random variable. In this case, those are the lowercase ANs. And then you multiply by the probability of the uppercase ANs. Right? Value times probability, sum over everything. That is the expectation. You can think of that as being the mean or the expected thing that you would get out of this random variable, this weighted average that tells you kind of what you should expect to see. Now, by the monotone class theorem, every positive random variable is the increasing limit of positive simple random variables. Great. Right? So if I have some x plus and h plus, some positive random variable, then I can make some increasing sequence of simple random variables xn such that xn is increasing to x plus. Again, this is the monotone class version of what measurable means. Increasing limit of simple functions. And then we can use this to find the expectation of a positive random variable. And then for general random variables, using the decomposition of random variables into positive and negative. So for the positive random variable, well, over here on this side of the equation, I can compute the expectation for every finite random variable, for every simple random variable. And then I can take the limit of that. And because these simple random variables are increasing, I know that that limit is also, well, that sequence is also increasing. So either that sequence converges or it diverges to infinity. Right? So it's possible that the expectation of this random variable is infinity, but it's also possible that it's some finite value. Now, if I have a generic random variable that can take positive values and negative values, Then we decompose it into its positive and negative parts, right? And then if the expectation of x plus and the expectation of x minus, notice that x minus is a positive random variable, even though we call it the negative part. No. But at any rate, if both of those are finite, right, or if both of them are not infinite, right, then we can talk about the expectation of the random variable x as the difference between the positive part and the expectation of the negative part. Of course, if they're both equal to infinity, you have an infinity minus infinity situation and all hell breaks loose. You're off the rails there. The expectation of a random variable is sometimes called the mean. A random variable with finite expectation, ooh, that's not quite right. A random variable has finite expectation of both the positive part and the negative part is called integrable. The set of integrable random variables is L1. If we need to indicate what they're measurable with respect to, we might call that L1 of H. And the condition that x is integrable is equivalent to the expectation that the absolute value of x, new random variable, is less than infinity. Right? So that's called L1. More generally, you can talk about LP. These are LP spaces. We won't have a whole lot of use for LP spaces, though we will see L2 a little bit later. Okay, the same thing is true for integration. I'm not going to go over this. This is just the same thing I talked about, but using the language of measurable functions instead of the language of random variables. Nothing really changes except language. All right. Now, we do need to talk about something. We need to talk about something that we can promptly ignore, or that I would like to argue that we can ignore. It is conceivable that in your sigma algebra H, there are events for which the probability of the event equals 0. Or correspondingly, if it's not a probability measure, it's just a measure for which the measure equals 0. These are called null sets, and null sets are not detectable by measures, right? Somehow, if it has measure 0, the measure is not seeing it. But nonetheless, they sometimes introduce complications in the analysis. These complications are usually best ignored. I mean, you can't always ignore them, but usually adding in null sets or taking out null sets doesn't really change the calculation, especially if what you're interested in is probabilities. So oftentimes you can ignore null sets. But we need some language for when we are ignoring null sets. That language we use is this word almost, right? So if we have an event that has probability 0, then we say that event almost never occurs, right? It's occurring with probability 0, but probability 0 does not mean impossible, just means you're never going to see it. I don't really know what the distinction is, but nonetheless, it is possible that you see a value from a random variable for which the probability that you saw that value is 0. So we say that almost never occurs. If, on the other hand, the probability of the event equals 1, we say that A almost surely occurs. And if we're in the measure theory situation, right? So if I have a set and the measure of the complement equals 0, then we say A is almost everywhere, right? Or almost nowhere if the measure of A equals 0. Two measurable functions, f and g, are equivalent or equivalent with respect to the measure mu. If the measure of the set where they do not agree equals 0. You can denote equivalence classes of f with this bracket, and same with random variables. And then it's easy to see that, well, it's an exercise, but it's not hard to see this exercise, that if you have two equivalent random variables, that their integrals are the same, or their expectations, if we're using the random variable language. All right. We are cruising through Haar and Lebesgue measure. We've talked about Lebesgue measure. But it turns out that we need some measures which are even more general than that, but generalized Lebesgue measure. So where we start is we say, oh, well, we have this measure on R. And this measure on R, basically, the Lebesgue measure is giving us lengths of intervals, right? Or if we have unions of those things, sums of lengths of intervals. And R, the real numbers under addition, are a group, obviously, right? And they're also a locally compact group. So locally compact just means that pick your favorite element in the set. You can find an open set around that, and that open set is in a compact set. You can find a compact set which contains that open set, right? Or put another way, well, that's fine. Basically, every point has a compact neighborhood for which it is in the interior, is another way of saying that. Locally compact groups can be topologized, right? So we can come up with the notion of neighborhoods and open sets in locally compact groups. And so we can take these open sets generated by this topology, and we can construct the Borel sigma algebra on G. So if I'm given a locally compact group G and I topologize it, then I make the sigma algebra from the open sets, and then I get a Borel sigma algebra on G. Now on R, the Lebesgue measure is the unique measure for which when you put in an interval, you get the length of the interval out. Great. It's very easy to see that, that this measure is translation invariant in the sense that if I take a set and I translate it anywhere on the real axis, I'm not changing the measure, the Lebesgue measure of that set. If I move an interval, it doesn't change the length, right? So this measure is called translation invariant, right? And it turns out that translation invariant Borel measures are almost uniquely determined, right? Almost uniquely determined. Let me show you why they're not completely determined. Suppose I gave you a new measure on R, and I said, well, let's make the measure of an interval twice the length of the interval. We could do that. Certainly, if I make every interval, I'm going to call the measure twice the length of the interval, then moving an interval doesn't change twice its length, right? And so that's an example of another measure which is translation invariant. But once you have a set with positive measure and you assign a value to that set, the translation invariant measure is unique. Right. So in other words, Lebesgue measure is the unique translation invariant Borel measure on R for which the unit interval has length 1. Once I tell you what the unit interval is, it has length 1. The measure is completely determined. It is translation invariant. And there is no other Borel measure which is translation invariant that takes 1 for the value of the unit interval. Great. This can be generalized to other locally compact abelian groups. Woo. This is actually a really beautiful theory, and I recommend that anybody who is interested in this stuff read up on it. It's the foundation for so much work in this area. Rudin has a really good book called Locally Compact Groups, I think is the name of it. So that's a good reference for it. Anyway. Okay, so if I have some other locally compact abelian group, G, right, and it has some operation plus, and because it's locally compact, it comes with a topology, and from the topology, we can make a sigma algebra, the Borel sigma algebra, right? Now, we can ask whether there are translation invariant measures on this set G, right? Plus, the fact that we have addition allows us to translate sets in the group. I can take my favorite set and add X to it, and that's going to move it to someplace else in the group. And I can ask, is there a measure for which the set that I started with and its translation always have the same measure? And the answer is yes, right? And And once you specify the measure of a single set with positive measure, right, kind of like we did in the real axis with the interval 0, 1, once you do that, right, then this translation invariant measure is uniquely determined. Right? This measure is called Haar measure on G, normalized on the set K, the compact set K that we ascribe a positive probability to. Oftentimes, the group G is compact itself. Imagine a torus, right? A torus is a lovely locally compact abelian group. As a matter of fact, it's a compact abelian group, right? And we can make a Haar probability measure on it by saying the measure of the entire group equals 1. Obviously, if the group is not compact, you can't do that. And you have to pick a favorite subset that you're going to use to normalize the measure. Okay. Okay. Well, one thing that you might experiment with and convince yourself of is we talked about Lebesgue measure on R. We can make Lebesgue measure on R2 by essentially looking at the product sigma algebra and then kind of a, well, you can make a product measure on that. And it turns out that when you do the product measure on Rn from Lebesgue measure, you just get Haar measure on the locally compact abelian group, which is Rn, right? So you don't get a new measure. Basically, Haar measure on Rn is the usual measure that you have been integrating functions with all your life, well, all your life since you've taken multivariable calculus. Okay. I'm not going to go into this, but I'll state the theorem. The proof is relatively easy. The reason that I say that you've been using Lebesgue measure your entire life is because if you have a Riemann integrable function, so for instance, if you have a continuous function or a function which is continuous except at a countable number of places, then the integral of f with respect to Lebesgue measure is equal to the integral of f, just the ordinary Riemann integral, right? And this could be on a subdomain. It doesn't have to be supported on all of R, right? And moreover, the same thing is true in Rm. As claimed, I said that you have been using Lebesgue measure on Rm your entire adult life. Well, that's because if you have a Riemann integrable function and you integrate it with respect to Lebesgue measure on Rm, or Haar measure on Rm, that's the same thing as just doing the iterated integral in good old-fashioned calculus. All right. So basically, this is saying that oftentimes, if you're dealing with Lebesgue measure, instead of doing this thing where you do integrals by kind of looking at limits of increasing sequences, if you know that your integral can also be written as a Riemann integral, then you can use fundamental theorem of calculus and all of those other tools, right? So this allows you in certain instances to translate a Lebesgue integral into a Riemann integral where you have lots more tools thanks to Leibniz and Cauchy and Newton and all of those guys. All right. Do apologize for the length of this introduction. Hopefully you're finding it interesting, or it's at least reminding you of some things that you have heard about before. Okay, so now suppose I have a probability space, omega, and suppose I have a real valued random variable. Well, if I have a real valued random variable and a probability measure, I can make a new measure on R. I'm going to call this mu sub x. Mu sub x on the Borel set A is just going to equal the probability that your random variable landed in that set A. Okay. So this is a measure on R, a Borel, well, a measure on R with respect to H. This is a measure on R, right, as opposed to the measure on your original sample space, omega. This can be useful because sometimes omega is big and complicated, right? And somehow changing that measure or finding a different associated measure on the real line is useful because, well, the real line is not that complicated, or at least we know a lot about it. Okay, so if I'm given any measure, right, any Borel measure, I can define the cumulative distribution function by looking at the measure of the set from minus infinity to x, and I call that capital F of x. If mu happens to be the distribution of a random variable, then I can write the cumulative distribution function as f sub x of little x is just the probability that my random variable takes a value less than or equal to little x. Cumulative distribution functions are non-decreasing. That's because measures are monotonic. Oops. The limit as we go to minus infinity equals 0. That's because, well, let's just look at this expression right here. Measure, there's nothing at minus infinity, right? And if f sub x is a cumulative distribution function for a random variable x, then as we go to positive infinity, the distribution function equals 1. Now, if you've seen a little bit of analysis, sometimes f is differentiable. Doesn't have to be, but if it is differentiable, then we write lowercase f for f prime. In this case, lowercase f is the Radon-Nicodemus derivative of mu. And so if you can do this, if you can compute the distribution function and you discover that it has a derivative, then the integral with respect to the measure mu is just given by the ordinary Riemann integral, where I take the same function g, but then I multiply by f of x dx. So again, this gives us a way when you have a Radon-Nicodemus derivative to integrate with respect to these distribution measures. When it exists, f sub x is called the probability density function of x. It doesn't have to exist, but when it does, it's the probability density function. And in this case, if I have a probability density function f sub x, then I can compute expectations by doing ordinary Riemann integrals. Ordinary Riemann integration, nothing more to do. All right, we're getting through this. We're going to get to someplace interesting before too long here, I promise. Well, I kind of find this stuff interesting too, but all right, we do have to talk about joint distributions now, right? Because eventually we are going to be talking about the random locations of a number of different particles living in the p-adics, right? So these random locations are random variables, and we're going to be dealing with multiple of them at once. And in our case, the locations of our random variables are going to be in general dependent on each other because they represent charged particles that are not going to want to get too close to each other. Right? So we need to be able to ascribe probabilities to situations where we have a random vector. Okay. So if I have a random vector, that basically means that each of the coordinates are random variables. Okay, likewise, now we can define the joint distribution of the random vector to be the measure on Rn, Borel set of Rn. It's defined exactly the same way. The measure of a set A, that's a big set in Rn, right, some blob, is just the probability that your random vector lands in that blob. Same definition as before. Just looks a little bit noisier, right? If I have an honest to God rectangle, so just a Cartesian product, right, then the probability that my random variable lands in that rectangle is going to be the integral over that rectangle of the distribution measure. Okay. We can also define a joint distribution function. Right, before we only had one random variable, so we really only had to worry that x was less than or equal to little x. Here, this is a function of several variables, but in each coordinate, it's basically just telling you, you want the random variable associated to that coordinate to be less than or equal to lowercase x of that coordinate. So this is a straightforward generalization. It's called the distribution function. If this thing is smooth, or at least has a derivative, then you can define the joint density function to be the partial derivative of the joint distribution function with respect to all of the variables. And then this theorem right here is basically just the analog to the theorem we had before. If you have a density function fx, then you can compute probabilities by integrating that density function, right, over the set A that you care about the probability of. And more generally, if you want the expectation of g of x, you can get that expectation by integrating the function g with respect to the density function. All right. Now, new things happen when we have more than one random variable. Quite frankly, it's just a more complicated situation. And so we need to be able to talk about, to develop some language that allows us to talk about multiple random variables at once. And again, this is important because we're going to have multiple locations of charged particles living in ZP at some point. And so we're going to have to be able to deal with them. So let's say this: if I have a random vector x, consists of the random variables x1 through xn. If I want the distribution just of the random variable x1, we will sometimes call this the marginal distribution, just to kind of give it a different name to indicate that we're talking about a subset of random variables that we are given. Then basically I can find the marginal distribution from the distribution by just saying, well, the marginal distribution of x1 at A, that's the probability that x1 falls into A, is mu sub the vector x, the distribution here, of A cross R dot 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 cross R. And think about what this is saying. This is saying the first coordinate is in A, the second coordinate is in R. That means I don't care where it is. Third coordinate's in R, don't care, etc. So basically these R's are just saying, integrate those things away, right? The only thing that matters is the first coordinate. There's nothing special about x1 here, right? I could find the marginal distribution of x2 by putting an R there and an A there, right? So all of these things can be found similarly. More generally, we can find marginal distributions of some subset of our coordinates, right? And you kind of do the same thing that you did before. You basically say, well, I'm going to take an event B and then I'm going to cross it with Rn minus n. This is basically saying I don't care where those other random variables are, right? When you're taking the expectation and R shows up, you're just saying, I'm going to integrate it away. And so, for instance, this is how you find the marginal distribution of x1 through x little n. You can do this for other subvectors. You just kind of have to be careful to ensure that you're taking into account, you know, where you're putting the R's and where you're putting the non-R's. But the idea is the same. There is a marginal distribution function as well. I don't really want to talk about that too much. Except to say that if there is a marginal distribution function, then there is sometimes called a marginal density function, which allows you to find probabilities by integrating that. I'm going to skip some of this right here because I don't think it's necessary. Okay. We are climbing through. We're almost done here. All right. Now I want to talk about a purely probabilistic concept called independence and conditioning. Not that this thing can't show up in analysis, it certainly can. And you see kind of corresponding facts to it in analysis, but it takes heightened importance in probability because we put certain thinking around what it means. It has a context in probability. So first, easy definition. If I'm given two sets in H, and I know the probability of B is not equal to 0, then the conditional probability of A given B is this equation right here, the probability of the intersection divided by the probability of A. This is something when I teach probability, I pretty much say this definition almost every day in that class. My students always laugh at me. They're always like, this again? I'm a big fan of repetition when it comes to teaching though. And this is an important concept. Now, two sets are independent if the probability of A given B just equals the probability of A, right? So we think about this conditional probability as saying, if I know the event B has occurred, what is the probability, right? Oh, I've made a mistake there, but okay, what is the probability that A will occur as well, right? So there should be a B right there, apologies. So if the probability of A given B is just the probability of A, that means A doesn't care about B. Whether or not B occurred is irrelevant, right? And that's the notion of independence, right? Again, this denominator here should be P of B. So equivalently, if P of A given B equals P of A, you can cross multiply and you find that an equivalent definition of independence is the probability of the intersection of any two events is equal to the product of probabilities. And more generally, if you can talk about independence for a collection of sets, right? So if I have a collection of events A, these things are said to be independent if for any finite subcollection, right? I pick my favorite subcollection that's finite, and I look at the probability of the intersection of all those things. If that's equal to the product of the probability of all those things for any finite subcollection, then we say that those random variables are independent. We can extend this notion a little bit by saying, basically, if I have a bunch of sigma algebras, we can say a collection of sigma algebras is an independency. A set of independent objects is an independency if, right, for every choice of sets, finite collections of sets from all of these different sigma algebras, if all of those things right there are independent, right? So you can read through this if you want, but basically, if you have this is a finite intersection, if for any finite intersection, the probability of that is the product of probabilities, for any collection that you pull from these sigma algebras, then you get an independency of sigma algebras. And basically, this is just saying, if I just have two of them, it's saying that, well, the probabilities for computing anything in this sigma algebra don't care about the probabilities of anything in this sigma algebra. I don't need to know anything over here. This doesn't help me to know anything here in order to compute the probabilities here, and vice versa. Okay, random variables are said to be independent if their sigma algebras are independent. And think about what this means, right? The sigma algebra generated by a random variable, you can kind of think of that as the pre-image of an interval, but it's a set of measurements that falls into some little 99 to 100 degrees, right? You have something over here. If those sets, the probability of those sets, if the probability of those sets is independent of the probability of, say, the inverse images of pressure, right? If pressure is saying nothing about temperature, then those two things don't affect each other, right? The pressure and temperature are independent of each other. All right, blah, 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 blah. And then, we have to do conditional densities. It's relatively easy to show that, or to check. One way of checking that something is an independency or a bunch of random variables are an independency is if the distribution measure for the random vector is the product of the marginal distributions, independence. Likewise, if you have the distribution function, right, and you can write the distribution function for the random vector as the product of distribution functions of the individual random variables, it's independent, right? Likewise for the density function. If there is a density function for your random vector and that thing can be written as the product of marginals, then you have independence. All right. Now, I'm not going to go through this a whole lot, except to say that one can rephrase, well, one can use the definition of conditional probability on sets generated by random variables, right? So we might talk about what is the probability that the random variable x takes a value little x, given that we know the random variable y takes the value little y. So for instance, what is the probability the temperature is 100, given the pressure is 1,000 millibars or whatever they measure pressure in, right? And then this is just the different definition of conditional probability for these events. It's the probability that x equals x, y equals y over f of y equals y. Well, okay, you can write all of those things in terms of the distribution measure, distribution function, or density function. I wrote it here for the density function here, but basically that numerator right there, the probability that x equals x and y equals y, well, the density function is playing the role right there, right? And the probability that y equals y is that thing right there. So oftentimes you can come up with a density function, which allows you to compute conditional probabilities of random variables. We'll use that a little bit, but not a lot. All right, conditional expectation. I'm not going to talk about conditional expectation, but I am going to, we're getting closer to where we want to be. Random processes and random fields. Okay. Let T be an index set. Okay, so usually this is a subset of Rn for some n, oftentimes it's a subset of R. And then we have a collection of random variables, one for each T in the index set. And if each of these random variables is on the same probability space, so they're all measurable with respect to the same H, then we call this a random process. So a random process is just a big collection of random variables. That's the most basic definition, is I have some index set and I have one random variable for every index in my index set, right? Now, there's another perspective for this, right? We can also think that for each omega, right? So for each outcome in my sample space, right? Well, I can think of the value of the Tth random variable, and I can view that as a function of T, right? I have a bunch of different random variables. These random variables are functions. If I plug the same omega in, then I get a new function out, and that function is random, right? Or at least I pick omega randomly and then plug it in. What I'm going to see out is going to be random as well. This function right here is sometimes called the trajectory of the process, especially when the index set is a subset of the reals, right? So when T is a subset of the reals, and usually this is all of the reals, or maybe the positive reals, or maybe it's discrete, maybe it's integers or positive integers. But at any rate, usually when we have a subset of the reals, then we think of T as a set of times, and we think of the random variable x sub T is the value of some observation at time T. Right? And so these trajectories are kind of following how the random variable is changing with time. Think of the stock market, right? Again, the stock market may not actually be random, but from the viewpoint of us human beings, there's far too much to know about how to make it deterministic, right? And so it's random for all intents and purposes. And if you're following your favorite stock, I don't know, maybe you're collecting Bitcoin these days for some reason. If you're following the price of Bitcoin, right, then that is the trajectory, right? The price of Bitcoin at any time, as far as you or I are concerned, is a random number that seems to be going down, 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 but is a random number, right? And then the price over time is the trajectory, right? We're not going to be talking about these temporal processes, these processes that evolve in time. That's a beautiful classic subject of probability. If you know anything about Markov chains or martingales, Brownian motion, Poisson processes, right? These things are temporal processes and a very beautiful, interesting area of mathematics. But we're going to be talking about spatial processes. So if our index set is a subset of Rn, right, then we often, and really it could be some other geometric object over here, right? Because eventually we're going to be doing this with zp to the n, right? But we think of these t's now as a set of locations in space, right, in Rn. And in this case, so every point in space, say we're in R3, has a random variable at it, right? This is called a spatial process, or sometimes a random field, right? So when you talk about random fields in physics, they are connected to this idea of having a quantity at every point in space. In this case, those quantities are random, right? And so, I mean, you can still make trajectories for this thing. It's just a little bit harder to visualize and understand what they're saying. All right. So we're going to talk about a certain kind of spatial process called a point process here in the next section. All right, now we're getting closer to where we want to be. So far, we really have just talked, I've given you basically the first quarter of a graduate class in probability in an hour and 24 minutes. There will not be a qualifying exam at the end of this, though, so don't worry. Okay. So, but now we're getting kind of closer to what I really want to talk about, which is p-adic electrostatics. And the first idea, and this is something maybe some people haven't seen. This is often not taught in an introduction to probability, even at the graduate level. So this might be new to you. So suppose we start with a measurable space, and then we're going to make the product space with the product sigma algebra. And then we're going to form a random, well, a vector. We're going to form a vector in x1 through xn. So we're thinking of this vector as living in En. And I want to think of that as the position of n points or particles, I'm going to call them, in E. Right? Now, the situation that we're going to be interested in, these particles are not going to be still, they're not going to be fixed, they're going to be random. So I can think of x1, the capital X's, as E-valued random variables representing the random positions of the particles. So for instance, I can start talking about what is the probability that, say, x1 is at little x1, right? And so these are possible places where the particle can live, and these are the random variables representing the particles. Now, in the very simplest situation, the particles are indistinguishable, and except at the very end where I'm going to wave my hands a little bit about ensembles with multiple charges. This is the situation we're going to be in. We're going to be in the situation where all of our particles are indistinguishable. And something happens here when all particles are indistinguishable, right? There are some events in my product sigma algebra that are not physical, that cannot be physically observed, right? So for instance, let's look at this event where I pick my favorite set A in E, and then I look at A cross E n minus 1, right? This is a perfectly lovely event in the product sigma algebra. It's a product of things. Each one of those is in the sigma algebra. It's great. In words, right, this event represents the event that the first particle, x1, is in the set A, right? And I don't care where the other particles are. They're just in E somewhere, right? But if the particles are indistinguishable, I can't say the first particle is in A, right? I don't have the ability to say what the first particle is. There's not a label on it which allows me to zoom in and say, oh, this is electron number 1, right? And so this is an example of an event that I cannot actually observe in the laboratory, right? It is an event in this lovely sigma algebra, but it's not something that I can see. So that's information that I don't have access to. So what we need to do is we actually need to move to a smaller sigma algebra, because we can't tell if the first particle is in A, but one thing that we can tell is if there is a particle in the set A, right? Is there some particle in there? That's something I can observe. right? So in order to basically not have extra events in our sigma algebra that are non-physical, that are not observable to us, we're going to move to a smaller sigma algebra. At first inspection, that might seem bad, but actually moving to a smaller sigma algebra makes problems easier because you have to look at fewer sets, quite frankly. You can say fewer things because there's fewer sets that you can say things about. But for instance, the set that I just talked about is not something that we should be talking about. So we should eschew it from a consideration. So here's how we're going to do this. All right. Given a set A in my sigma algebra E, let n sub A count the number of particles that are in A. Really, these should be lowercase or uppercase x's. These are random variables. N sub A is a random variable, and that random variable is telling you, right, what is the number of particles that land in your set A. That is something we can observe, right? So n sub A just counts the number of particles in A, and then I can define the cylinder sigma algebra, weird name, but the cylinder sigma algebra on En to be the sigma algebra generated by these NAs. So basically, this is the smallest sigma algebra that allows you to count how many particles are in any particular subset of E, right? And really, if our particles are indistinguishable, that's all we can do. Right? We don't, unless there's some additional information about those particles that's not built into the system right now, right? Then that's the best we can do is just count how many particles land in various sets. And this sigma algebra is the smallest sigma algebra that contains all of that information. All right, and so a point process is just a probability space, right, where I have some set E to the n, so some Cartesian product. I have a sigma algebra, which allows me to get counts of particles, counting how many particles live in any particular subset, measurable subset, and then a probability measure. So basically, a point process is something that allows me to assign probabilities to events in the cylinder sigma algebra. And events in the cylinder sigma algebra, well, they're intersections of unions of complicated things, but a basic cylinder set is what happens when I just take a bunch of disjoint sets, A1 through AM, and I ask, well, when do I have little n1 particles in A1? When do I have little n2 particles in A2? When do I have little nm particles in AM? Right? This is a simple cylinder set. It's a cylinder set. Simple just means that it can be described with just one set of equations right here, and there's only a finite number of neighborhoods that I'm looking in. Right? There are more generic cylinder sets out there. However, the simple cylinder sets form a pi system, and since they form a pi system, once I know how to assign probabilities to the simple cylinder sets, I can do anything I want. Right? So we're going to focus on the simple cylinder sets. Quite frankly, they're what human beings care about, generally. Okay. So I'm going to go over this just very quickly, only because it kind of gives a little background to how I got into the problem. But we're not really going to use joint intensities or correlation functions, but they are nonetheless important. Right. So suppose what we want to do is look at the product of all of those counting functions, and then looking at the expectation of the product of a bunch of counting functions. Now, let's just think about this if we have two sets A1 and A2. Suppose we have two sets A1 and A2. They're disjoint, right? And then I'm looking at the expected number of particles in this set times the expected number of particles in this set over here, right? Now, imagine these sets are actually really small, right? Imagine these sets are really small, and imagine, just for the sake of argument, that they're so small that, you know, with really high probability, the number of particles in this small set is 0 or 1, and the number of particles in this small set is 0 or 1 as well. So let's just suppose that, we have zoomed in sufficiently that, with low probability, will you have more than one particle in each one of these two sets? All right, then the product of n sub a1 and n sub a2 is equal 0 unless there is one particle in each one of those sets, in which case it's 1, right? So what this is basically telling you, right, is the expected number of pairs for which one of the elements is in one set and the other element is in the other set, right? This is pair correlation, right? We're trying to see, well, if those two sets were close to each other and these particles were charged, you would expect the expected number of pairs in both of those little neighborhoods, if they're close together, to be really small, right? Charged particles want to stay away from each other. Whereas if I have a small set here and then a small set, really, really far away, then we might get something which is almost independent, right? If these things are charged, but this thing is really far away, it's not really influencing a lot of any particles that might be in this neighborhood, right? And so this, when I have just two sets, the expectation of the counting functions for those two sets, the product of the counting functions for those two sets is pair correlation. And more generally, if I have m sets, then I get the mth correlation, right? I have m little sets. What is the probability? Again, if these are small under our simplifying assumptions, what is the probability that you have one particle in each one of these n sets, right? That's roughly the information which is contained in these correlation functions. So if there is a measure, rho m, so that whenever I have my favorite collection of disjoint sets, right, if I want to compute the expectation of the product of the counting functions, if there's a measure such that when I plug in the rectangle into that measure, then we call that measure the mth joint intensity measure of the process. And we'll talk a little bit about the word intensity maybe later, but just the name. All right, now sometimes you have a joint intensity measure for the process. Sometimes the set E that you cared about is a locally compact abelian group. For instance, it might be R or Rn or ZP or ZPn, right? But at any rate, then it is possible that there is some Borel measurable functions, Rm, such that the expectation of the product of the counting functions is the integral over that rectangle of Rm. That is, it's possible that if you have a Haar measure, that this joint intensity measure has a Radon-Nicodemus derivative with respect to your Haar measure, in which case you get a function out, and that function is called the correlation function, the mth correlation function of the process. Okay, and this is useful because, for instance, if you're in the case where you have real numbers in the Borel set, right? For instance, if I have a correlation function and I actually want to compute these expectations, then I can integrate that correlation function over the rectangle, and then this is just regular integration, Riemann integration, multivariable calculus, something you've been doing your whole life. Right? So having correlation functions is useful. And having correlation measures is useful too, just a little bit less useful. Let's talk about the 1-point function. It's kind of the easiest one, right? Well, one thing to say is from the definition of intensity measures, if I look at the number of particles in my entire set, that's n, right? I have n particles in my entire set. And so if I look at the expectation of that, then on one hand, it equals n, and on the other hand, it is the integral of the first correlation measure, right? Or if this first correlation measure has a correlation function, it's the 1 over n times the integral of the correlation function, right? And this thing equals 1, right? Because again, we're asking about the expected number of particles in the entire set. We know how many particles we've put in there. Right? So if it shows that that rho sub 1 divided by n is a probability measure with density function R1 divided by n. That's the density function. And basically, what information is this telling us, right? This says that the probability that at least one particle lies in A is given by the integral 1 over n times the integral of R1 of x, right? Now, what is this saying, right? What this is saying is that this is giving us the spatial density of particles, right? This is saying, I just care about, is there a particle in this little window or not, right? That's just the spatial density, right? If I were just trying to kind of make a histogram or some sort of density graph of where the particles lie, right? So the first correlation function divided by capital N tells you the spatial density of particles. That's already really useful if you can get your hands on it. All right. So I think that's the end of the probability section. Maybe I'll stop and see if there are any questions here. I know that we're creeping up on the end of the first session, but if there's any questions out there, please just pipe up and I'm happy to answer them. Otherwise, I will just keep going.
So, any question? Guys? It seems that everything is clear, right? Also in the chat.
Okay. All right. Well, then I will continue. This section, you're going to see a bunch of stuff that you're seeing in another lecture. Hopefully, this is complementary to that, right? But everything you're going to see here, you've probably seen before. Nonetheless, you know, I kind of think of mathematics, especially the learning of mathematics, as kind of like refinishing furniture. Right? You have to keep going over it, right? Sanding out the rough spots and kind of go over it again and again. So even if this is something you've seen before, or maybe it's something you spend your life studying, still, you know, there's some use to refinishing the furniture. So I'm going to start someplace which is very near and dear to my heart. And this is absolute values on Q. You know, I should tell you a little bit about my history. I started out as a number theorist, and then random matrix theory and probability. And now I'm doing kind of this intersection of number theory, random matrix theory, and probability. But this is close to where I started my tour of mathematics at a young age, and that's absolute values on Q. Now, I'll go through this fast. An absolute value is a function on Q, which is positive definite. So it's positive except at 0, where it's 0 is multiplicative and satisfies the triangle inequality. It turns out that the usual absolute value has this nice property that, you know, for every integer n, there's some x in Q between n and n minus 1. This basically says that the integers are marching off to infinity with respect to the usual absolute value. There is a really dumb absolute value called the trivial absolute value. It takes the absolute value of 0 is 0 as it needs to be, and the absolute value of every other number is 1. Generally, we don't really play with the trivial absolute value very much. It's not very interesting. Certainly easy to compute with, though. Now, if I have a rational number x, okay, and my favorite prime p, then I can factor my integer x to be plus or minus p to the m times a over b, well, where a and b don't have any factors of p. Right? Basically, all I'm saying is that I can take all the factors of p that appear in the factorization of a rational number and pull them out front, and I get a p to the m. It's possible that m is positive or negative. Right? If we assume that everything is in lowest common terms, then we define the p-adic absolute value to be, well, in this case right here, you basically take the exponent on the p and put it into a minus sign and ignore everything else. Okay, I claim this is an absolute value. I'm sure you've seen that proof, or if not, you can convince yourself. It's not hard. But it's also true that the p-adic absolute value satisfies something stronger than the triangle inequality. One of the words for this summer school is ultrametric. So this is sometimes called the ultrametric inequality or the strong triangle inequality. And it just says that the absolute value of x plus y is less than or equal to the max of those absolute values. Okay. This is called a non-Archimedean absolute value, if it satisfies that, because we don't have the Archimedean property of the integers. Something you've probably seen, but is really a beautiful theorem. If I have two different absolute values on Q, it's possible that they're related by one being a power of the other. Right? That's one thing you can do to make a new absolute value from an old one is pick an appropriate power. Not every power is going to work, but pick an appropriate power and you can get a new absolute value from old. And we're going to say that any two absolute values that differ by that sort of raising to a power are equivalent, right? So you can make an equivalence relations on absolute values. And then an equivalence class under that equivalence relation is called a place of Q. Fun exercise, not too hard. If P and Q are different primes, you can show that the absolute value of P is not equivalent to the absolute value of Q. All right, now there's a really important theorem, which I think of as a number theory theorem. It's Ostrowski's theorem. And what it says is if we start with our favorite non-trivial absolute value, again, throw that thing in the garbage. We don't care about it. Start with your favorite non-trivial absolute value on Q. Then that absolute value is either equivalent to the usual absolute value, the one you've been using your whole life, or it's equivalent to one of the p-adic absolute values, right? So basically what this says is that the absolute values on Q are in correspondence with the primes. Well, except for the usual absolute value. And so sometimes we throw infinity into our list of primes and we call that the prime at infinity, right? So if you wanted a direct correspondence between primes and absolute values, you would have to throw in infinity. But basically, except for the usual absolute value, each absolute value is equivalent to one of the p-adic absolute values. Now, this is brilliant. This is beautiful. This is the thing that's cool about this is it gives you an analytic way of studying the primes. One way of studying the primes is studying the absolute values on Q. Now, this may seem miraculous, and it kind of is, but when you see the proof of Ostrowski's theorem, which I'm not going to go through, you do see how factorization comes in, and you see how this all works, right? It's not that these absolute values are independent of prime factorization. Prime factorization is kind of what makes Ostrowski's theorem work. But nonetheless, you can start by axiomatizing purely analytic objects, right? There's nothing algebraic about how we defined our absolute values on Q. Start with those just purely analytic objects, and then learn things about prime numbers by studying those absolute values. Beautiful. Okay, I'm going to move to completions of Q. All right. So there are various ways of constructing the p-adic numbers, or for that matter, the real numbers. I think the best way is the Cauchy completion model. Again, this is probably something you've seen, but if so, let's just refinish the furniture together. First, if I have a sequence of rational numbers, right here, I'm using just for now, I'm just using the absolute value to be the usual absolute value. But a sequence of rational numbers is Cauchy if, given an epsilon, there exists a capital N, such that when you go out into the series past that capital N, that the two terms out there are, well, smaller than epsilon. Right. This just says that as you go farther out a Cauchy sequence, the terms get closer and closer to each other. Now, you probably remember from analysis as an undergraduate that Cauchy sequences are convergent, right? Yay, that's pretty cool. However, here's the problem, is that if you have a sequence of rational numbers that is Cauchy, it is convergent, but it might not converge to another rational number, right? I mean, think of a sequence which converges to pi. You can make a sequence of rational numbers which converges to something which is not rational. And so we want to have the idea of what a convergent sequence is without referring to the limit, right? Because if we want to construct the real numbers, we can't use the real numbers in the construction. So we have to be able to say, oh, this sequence converges to something without talking about what that thing is, because if that thing is a real number, we have not defined it yet, right? So this is where Cauchy comes in, right? Now, one thing that we can tell is we can determine when sequences converge to 0, right? That's not hard for us to tell. There's a definition that says convergence to 0. So I can determine whether or not my sequence of Cauchy, my Cauchy sequence is converging to 0 or not. And we're going to say that two sequences are equivalent if their difference converges to 0. Okay. So basically what we're saying is we're taking two Cauchy sequences and we're saying they're equivalent if their difference converges to 0, but this is kind of in the background implicitly saying, right, these two sequences, Cauchy sequences, are converging to the same thing. We just need a way of talking about what that thing is. All right, so anyways, we have an equivalence class. You can prove it's an equivalence class, not hard, or equivalence relation. The set of equivalence classes, right, I just put square brackets around it. But basically, that is just a collection of a bunch of different Cauchy sequences, any two of which their difference converges to 0. Okay, here's the definition. The set of equivalence classes is called the Cauchy completion of Q with respect to the absolute value, right? When this is the usual absolute value, then the Cauchy completion of Q is the real numbers, right? So I'm telling you that the real numbers are equivalence classes of Cauchy sequences. Now, you probably don't think of the real numbers that way, right? If at all, if you think about a generic real number, you probably think about its decimal expansion, right? I mean, that's one way to think about it. So let's just take the number pi, not a rational number, has a decimal expansion. I can make that decimal expansion into a Cauchy sequence. One way of doing that would just have the sequence 3, 3.1, 3.14, 3.141, right? You could just do the digit-wise expansion, and you would get a Cauchy sequence which converges to the number pi, right? Now, suppose I have some other Cauchy sequence which converges to the number pi. Well, if those two sequences converge to the number pi, then their difference converges to 0, and so those things are equivalent, right? So this is one representation for the Cauchy sequence that represents the real number pi. Now, there's lots of other ways of making Cauchy sequence. For instance, I can expand pi in a base that's not equal to 10. I don't know, base 11. It's a crazy thing to do, but you could do it if you wanted to, right? And then I could write down x as the decimal expansion in that base, right? And then I can make a Cauchy sequence from those digits and that base, right? And that's going to be, well, if you expand pi, right, you would get a different representation for pi, a different Cauchy sequence, but it represents the same real number. All right, I'm going to aim to wrap up here in 4 minutes so I don't keep us too long. Is that okay? So you might say, okay, great. You've told me that the real numbers are Cauchy sequences, right? You probably like, that doesn't sound useful to me. I think of the real numbers as a field, right? And Cauchy sequences, how are they a field? Well, we have the limit laws, right? I have limit laws that tell me how to add two Cauchy sequences and subtract two Cauchy sequences and multiply and divide two Cauchy sequences. Well, as long as I'm careful about denominators with division, right? So I have the ability to add, subtract, multiply, and divide Cauchy sequences. And it turns out that these things are well defined on equivalence classes, right? So it doesn't matter the representative which Cauchy sequence I use. If I look at the the class of an plus bn, that's going to equal the class of an plus the class of bn. So it's the limit laws that allow us to move the algebraic operations onto the Cauchy sequences. Right. All right. So now let's just do the same thing with, instead of the usual absolute value, let's use the p-adic absolute value. Okay, the Cauchy completion of Q with respect to the p-adic absolute value is called the p-adic rational numbers, denoted Q sub p. It is a field. And in spite of the fact that the construction is almost identical to the real numbers, these are very different numbers, right? And the reason is because just because a Cauchy sequence is Cauchy with respect to the usual absolute value absolutely does not mean that it's Cauchy with respect to a p-adic absolute value, and vice versa, right? You just get different collections of Cauchy sequences. And so you get completely different objects. So one immediate observation is, let's suppose we just take a sequence of integers, right? Just regular integers. Then the only way a sequence of integers can be Cauchy with respect to the usual absolute value is if that sequence of integers is eventually constant, right? Integers don't have other integers in their neighborhood. So, right. And so that means we don't get anything new by doing the Cauchy completion of Z with respect to the usual absolute value. You already have the integers, you just get integers out. Nothing new happens. On the other hand, right, if I have a finite prime P, right, it is possible that a sequence of integers converges to a non-integer p-adic rational number, right? In other words, and we'll see why this is true in when we come back this afternoon, but basically the integers form a dense, well, they are dense in a certain subset of QP, right? So the closure of the algebraic, sorry, of the integers is a, well, it's an open set and a closed set, but it actually, you can find limits of integers that converge to things in the p-adics. We'll see why this is true this afternoon. So in order to not burden everybody, I know you've been sitting still for a long time. I will stop here. I'll come back this afternoon and start right here. I'm happy to answer questions, or feel free to engage me either via email or after this as well. And I'm always happy to talk about this. But if there's any questions out there on things I've talked about so far, I'm happy to answer them.
Are there questions or comments? No, we don't have questions at this moment.
Okay, well, thank you. I will stop sharing my screen. And I think if my calendar is correct, we come back in 2 hours and 5 minutes.
Yes, see you.
Great. Thank you, everybody. See you this afternoon.
Había algo que ahí iban a preguntar sobre Ángel, ¿el correo? Que tiene que ser algo urgente. Roxana le mandó un correo que tiene que mandar algo urgente.
Bueno. Voy a hacerle como los niños que me van a poner a cantar.
Curso 4, 2 horas, hizo la conferencia de 5 a 6:30. Y vamos a descansar. ¿Y tú sabes si esto se puede ver la diferencia?
Lo abren y paso el terreno. Polvo. Sí, lo abren. De hecho, aquí, bueno, antes de la. Ahí hay otro camino. Subimos a los dos direcciones. Y ahí
Fin de semana, una actividad de fin de semana, a ver qué celular.
no tiene nada.
Pues no, es el botón, y me gusta porque lo tengo hace años, o sea, sí le he dado golpes, pero sí, vamos a cambiarlo, no sé. Sí. No, eso es un santo. Claro, sí. Yo lo que quiero es. O sea, yo digo, si quiere hacer las cosas, que tiene una posibilidad. Es el problema.
Ellos su experiencia. Entonces las becas también. En realidad. No me quieren, porque piensan que hemos cumplido las becas que
Entonces, nunca me había claro. Francia. Una vez, en una posición, pero la señores le habla y si te pasa ya.
no es mucho.
Sí, no. Cuando yo pensé cierto, y
Recién doctorado.
y los profesores de universidad, pero alguna vez estaba hablando con. Dice que no había, digamos, tolerancia. No, o sea, que sí por auge en una universidad, pero pues escribí.
Y además sería que también
Es un país más fácil de Estados Unidos. Estados Unidos es lo que sabes que manda.
lo que sí siento es que si estuvieras en Francia, entonces independientemente bueno, puedes hacer la trayectoria y
Ya te lo doy. Ah, sí. Ah, Iniciamos. Iniciamos. Iniciamos.
Okay, ready? I'm going to start recording.
Great. All right.
Wait a second. Okay. So thank you very much, everybody. We continue with the course of Professor Chris Sinclair, sorry. And then thank you.
Thank you, everybody. Can everybody hear me out there all right? Okay, good. Yeah, so I was informed after the first session that it would be smart of me to give you a little break after 50 minutes. Apologies. I know it's a long time to sit and listen to mathematics, so I will throw in a break after about 50 minutes. So we talked this morning about Cauchy completion, and now I would like to talk about we talked about Cauchy completions with respect to the p-adic absolute value. I want to kind of finish up this section with 3 theorems, all of which are fairly trivial, but demonstrate kind of the importance of Ostrowski's theorem. The first just says that the Cauchy completion of Q with respect to the trivial absolute value is Q. It doesn't give you anything new. That's easy to see. So that's not a new completion. It's something we already know and understand. The second theorem says that if we have 2 equivalent absolute values, right, so that one is the power of the other, then their Cauchy completions are the same. And this is because basically changing one absolute value to another by raising to a power doesn't change the Cauchy. Basically, it changes maybe how far out you need to go before you know your terms are within epsilon of each other, but it doesn't change whether or not the terms are getting close ultimately. And then finally, if we have 2 different absolute values, so 2 different places, this could be the P and Q, one of them could be infinity. So one of these could be the usual absolute value. But at any rate, given 2 different absolute values in 2 different places, then there is a sequence of rational numbers which is Cauchy with respect to one, but not Cauchy with respect to the other. Right. What this means is that their limits are essentially different, and so that you get different new numbers from equivalence classes of Cauchy sequences in, say, QP than you do in Q sub Q. All right. Okay, next. I will, wait a minute, share my screen. I'm sorry, I thought that I had it up. Apologies for that. All right. Okay, next topology. All right. So now suppose we have QP, right? Basically, two ways to think about this so far. One is equivalence classes of Cauchy sequences. Alternately, we can kind of think of the QP as being these new numbers that we get as the limit of Cauchy sequences. Well, okay, if we have a Cauchy sequence, then I can extend the notion of absolute value, p-adic absolute value, to that Cauchy sequence just by taking the limit in absolute value of the Cauchy sequence. Right? So basically what's happening here is Q has a nice absolute value, the p-adic absolute value. Q is dense in its completion, and therefore you can extend the absolute value to its completion essentially through continuity. Right? So that p-adic absolute value actually gets attached to this larger thing, not just an absolute value on Q, but an absolute value on QP. Right? This absolute value produces a metric. So I can say the distance between 2 points, the p-adic distance between 2 points, is just the absolute value of their difference, their p-adic absolute value of their difference. And so we have a metric, and from this we can construct a metric topology, right? So basically, how do you construct a metric topology? You take all of the balls with respect to that metric, and you call all the open balls open sets, and you generate the topology generated by those open sets. Right? So once you have a distance, you have balls. Once you have a bunch of balls, you have a topology. Once you have that topology, of course, you can make a sigma algebra, and that would be the Borel sigma algebra in this case. All right, so let's just remind ourselves just a little bit about what a topology is. A topology is very similar to a sigma algebra. It's a collection of sets that topologists use for a certain purpose, much like the sigma algebra is a collection of events that a probabilist uses for a certain purpose. And whereas, the probabilist or the analyst calls those special sets events or measurable, the topologist calls their special sets open. And basically the axioms for a topology is that the collection of these open sets could be closed under arbitrary unions and finite intersections. The axioms are a little bit different from sigma algebras, but they're very similar. Okay, balls. So if we want to look at the ball of radius r, the open ball of radius r about x, it's just a set of things that have distance less than r from x, so p-adic distance. These form our basic open neighborhoods. Okay. And we can also define closed balls as well. Nothing really changes there, except we kind of add the boundary. Right? We've already run into one closed ball, ZP, right? The set of integers is ZP is the closed ball of radius 1 centered at 0, right? So you can kind of think of ZP as being the closed unit ball in QP. Right? Well, things are different in the p-adics than they are in the reals because of the strong triangle inequality, essentially, something that we'll see again and again. And the p-adic absolute value is discrete, right? Every value of the p-adic absolute value is some power of p. Right? And what that means is that you can see any ball in QP or in ZP, but at any ball in the p-adics can either be viewed as a closed ball or as an open ball, right? So for instance, if I pick R to be a number between p to the n and p to the n plus 1, right? And I look at the ball, well, that's actually just equal to the closed ball of radius p to the n, right? Because there's no values of the absolute value between p to the n and p to the n plus 1. Right? So in particular, every single ball in the p-adics is both closed and open, or sometimes people say clopen, right? So let's just look at some of the differences between the balls in the p-adics and the balls in the real on the real axis or in some Euclidean space. So one consequence of the strong triangle inequality, if I pick any point in the ball, that ball has equal right to be called, so that point has equal right to be called the center of the ball. That is, if I pick some other point y in a ball of a certain radius about x, well, then that ball of that radius around x is also equal to that ball of that radius around y, right? Every point in a ball is the center of the ball. Very different than what happens in the Euclidean space, right? If I have two balls in QP, right? So if I have two of them, then either their intersection is empty, so either those two balls are disjoint, right? Or one is nested in the other, right? So if one is nested in the other, that means the intersection is equal to one of them. So the balls are much different in the sense that you can't have two balls that kind of overlap in your kind of traditional Venn diagram, that you know you would see in an undergraduate set theory class. You don't get intersections like that, right? Either the intersection is empty or one of the balls is contained in the other ball. The complement of a ball is also clopin, right? And so if x and y are in disjoint balls, then there exists a ball B such that x is in the ball and y is in the complement, right? And QP is the union of the ball and its complement. This is the definition of being totally disconnected with respect to the topology T, right? This is a very different condition than the reals or Euclidean space, which are completely connected. The p-adics are totally disconnected. Sometimes it is useful to introduce some more granular topologies on QP, right? So for instance, in QP, you can look at the topology generated by all balls of radius, say p to the minus n, right? This is the nth resolution of QP, right? And because balls don't overlap, right, they're either disjoint or one is inside the other. What this means is that you don't get anything of smaller radius in that resolution, right? This is very different than what happens in R. Like imagine that you took all of the open intervals in R that have, say, length 1, right? Well, that's actually enough to generate the entire topology on R, because if you take two things of length 1, you can intersect them to find much smaller open sets, right? As a matter of fact, through unions, complements, and intersections, you can get any open set you want. That does not work in the p-adics. If you have a resolution like this, then that sigma algebra actually turns out to be if you're in ZP, turns out to be a finite sigma algebra. There's finitely many sets in the sigma algebra when you look at the resolution on ZP. All right. Finally, we observe that QP is locally compact and ZP is itself compact, right? Why is that? Because every point I can find a ball around it. That ball happens to already be clopin, which means that it is a compact set containing an open set and your point is in the middle, right? Or somewhere in there, right? And so that says that QP is locally compact. It's a locally compact abelian group. As a matter of fact, it's a locally compact ring field for that matter. This is useful because we're going to be doing integration. We're going to make measures on those, and a locally compact abelian group has a translation invariant measure, which we will talk about in a couple sections. All right, so QP is locally compact. All right, so we've so far kind of seen a couple views of the p-adics. One was a construction, the Cauchy completion, using pretty pure undergraduate analysis with the addition of the p-adic absolute value, but except for that. So we have kind of this view of the p-adics. We have this topology view, right? We kind of understand there's a metric topology and we can talk about balls. And so we have kind of an idea of what the topology of this thing looks like. I'm going to move to the algebra. Okay, now we're looking at ZP. Okay, so we will eventually be restricting ourselves to ZP because it is compact. But remember, ZP can be viewed as a couple of different things. Either it is the unit ball, the closed unit ball in the p-adics. Okay, that's one way of thinking about ZP. It is also the completion of the integers themselves with respect to the p-adic absolute value, right? So if you just started with integer sequences and formed the Cauchy completions with respect to the p-adic absolute value, right, then you would get ZP, right? If you have rational sequences, then you get QP. Integer sequences give you ZP. So here's a theorem kind of explaining some of the algebra and the p-adics. First, ZP is sometimes called the ring of integers, and ZP is a ring under addition and multiplication. Right? Now, this is fairly easy to see that it's closed under multiplication. Right? Everything in ZP has absolute value less than or equal to 1. So the product of two things has absolute value less than or equal to 1. Right? But the strong triangle inequality also means it's closed under addition, right? Because if two things have absolute value 1 or less than or equal to absolute value 1, right, the absolute value of their sum is less than or equal to the max of their absolute values. Right? So the ZP is in fact a ring. There's a unique maximal ideal in ZP. This is the open unit ball, right? This is equal to PZP, right? So this is basically equal to all of the things that are in the unit ball, but don't have absolute value 1, right? The open unit ball is kind of the middle of the ball. And so if we throw away things that have absolute value 1, anything else that has absolute value less than 1 is divisible by some power of P. Right? And so this is this PZP. And this is a unique maximal ideal because, again, you can show that it's a ring, and you can show that if you have something that has absolute value 1 and you multiply it by something that has absolute value less than 1, you get something which has absolute value less than 1. It absorbs under multiplication. So we have a unique maximal ideal. You can mod out once you have an ideal. You can mod out by that ideal. It turns out that you get a field in this case because it's a maximal ideal. And when you mod out by a maximal ideal, you know you get a field. This is called the residue class field. In this case, it's just the finite field with P elements, Z mod PZ. And then finally, the group of units in ZP. This is the boundary of the closed unit ball. This is the set of things that do have absolute value 1. Right? This thing right here is a group under multiplication, but in general, it's not a group under addition, right? It's only multiplication that gets preserved because the product of two things with absolute value 1 has absolute value 1. All right. So those are just some things about the algebraic structure, and we will be using, PZP. It is important. This unique maximal ideal is extremely important, so we will be seeing it in the future. All right. So I want to give just a quick rundown of a algebraic construction of ZP. So here, this is called the inverse limit construction. And basically, if we have a sequence of rings, so just a bunch of rings, and then we have for any two indices in the sequence, I and j, we have some sort of homomorphism, phi ij from aj to ai. So we have these maps going from things that are farther out the sequence to things that are less far out the sequence. What we want is well, phi of I to be the identity isomorphism. That seems quite reasonable. And then we want also that if we have, 3 different indices, that essentially that we can write phi of from k to I as equaling phi from k to j first, and then phi from j to I. Essentially what this means is if you were to draw arrows between all of the different A's, is that those arrows representing phi ij, you would get a bunch of little commutative diagrams, right? You can factor through any intermediate place. Okay. So if I'm given my collection of rings and I'm given these connecting homomorphisms, then the inverse limit of the rings with respect to the homomorphisms are given by it's going to be an infinite tuple, right, of elements such that AI always equals the projection or the homomorphism from the J thing down onto the I thing for all I less than J. So, I mean, essentially what you can think of is we have a bunch of rings and they're kind of getting more and more complicated as we go up, right? They're kind of maybe getting bigger and bigger in some sense, right? And what a inverse limit is going to be is it's going to be a tuple, one element from each ring, right? But we want the elements in that tuple to be connected by these homomorphisms, right? So that if I have an element here out here at J in the tuple, and I have an element here I in the tuple, if I hit J with the homomorphism, phi goes from J to I, that's going to take me to the ith one, right? So it is an infinite tuple of elements in the rings, right? But they're connected in a very specific way. An arbitrary tuple is just not going to do the job. It turns out that this thing is a ring, and it's a ring under component-wise addition and multiplication. Right? I have these infinite tuples, each one of them lives in a ring, and so I can multiply at the same places or I can add at the same places. This gives me a new way of producing tuples from old tuples, right? And one has to check that the homomorphism properties still work, but they do because they're homomorphisms, basically. All right, so what we want to do is we want to see ZP as an inverse limit, right? This is a purely algebraic construction. There is this limit notation, but you know, it's not really an analysis type limit, except that we have this infinite tuple. So what I'm going to do is I'm going to start, my rings are just going to be Z mod P to the NZ, right? So these cyclic groups, these cyclic P groups, right? And so I start with just Z mod PZ, and then I have Z mod P squared Z, and then Z mod P cubed Z. Right, so I have more complicated cyclic groups. They're all P groups. Now I need to define some connecting homomorphisms. So the maps that go from Z mod PJZ to Z mod P to the IZ. Well, okay, if we look at an element in P to the JZ, it's just a coset that looks like this. Right, and so I can define phi ij to, well, I'll just take that A that I had before and put it in front of a PIZ, right? If you're actually using representatives, like if you're using the most common representatives for the elements in Z mod P to the JZ, this should actually start at 0, I suppose. But at any rate, if you're using the traditional representatives or Z mod P to the JZ, then another way of doing this is to look at that number right there and compute the remainder of the representative when dividing by P to the I. Right, so there's kind of a division algorithm way of calculating this as well. Okay. Well, then the inverse limit of Z mod P to the NZ with respect to these homomorphisms, these connecting homomorphisms, is isomorphic to ZP. And I'll show you an explicit isomorphism once I give you yet another formulation of ZP. But we need some tools here before I can show you how these things line up. Okay, now I do want to talk a little bit about cosets and balls. Right, we've already observed that ZP is the closed unit ball in QP, and the maximal ideal PZP is the open unit ball. Right. Sometimes this open unit ball is clopin. So sometimes it's useful to think of it instead of as an open unit ball, as a closed unit ball. And I can do that. So I can also think of it as the closed unit ball of radius P inverse, right? Everything in PZP is divisible by P. P has absolute value 1 over P. So everything has absolute value less than or equal to 1 over P. Right. And so the cosets of PZP correspond to the closed balls of radius 1 over P. Right? So I can talk about the cosets as a ball, a closed ball if I want, or I can talk about it as a coset, right? One hand, it's talking about the topology of the object. The other is talking about the algebra of the object. This goes further, right? If I have a closed ball of radius p to the minus n in ZP, so some little ball, right? Then it turns out that if it has radius p to the minus n, then b is a coset of p to the n ZP, right? So I can make, instead of looking at the maximal ideal, I can make a much smaller ideal, p to the n ZP. And then this closed ball is essentially a translation of that much smaller coset. So every ball in the p-adics in ZP is a coset, right, of some form, right, at some level. So series expansions, I'll go through this fairly quickly because you've probably seen a lot of this before. A p-adic integer is an equivalence class of Cauchy sequences, right? One way to make Cauchy sequences is to look at series, right? I mean, you can, if we have a series that converges fast enough, well, then it produces a sequence of partial sums, right? So one way of doing that is looking at series. And here's the series that we're going to consider, right? Is essentially if I have my favorite integer m, so I'm going to just start with integers first. If I have my favorite integer m, I can write it base p, and then m is going to be, well, some coefficients that depend on m times powers of p. That's just the base p expansion. Right, and I can do this in such a way that the digits are between 0 and p minus 1. Right. Well, okay. What I can do is how do I want to say this? So one way of extending this, essentially what I've told you is a way of writing any integer as a series. Well, if I want to write any arbitrary p-adic integer, right, Cauchy sequence, as a series, what I can do is I can take a limit of those integers, right, and then look at the series formed from those integers, right, and that should, well, it should be Cauchy if that thing is supposed to represent a p-adic number. Right. So there's a little bit of construction that goes into this. I'm not going to go too deeply into it because you probably are seeing it in other aspects of courses here. But what I want to say is basically that if I have an element x in ZP, I can find a series for it such that the coefficients are between 0 and p minus 1. And this is a base p expansion, so I have powers of p to the n. This is called the canonical series representation for elements in ZP. The canonical part comes because really our choice of 0 through p minus 1 as the representatives of the cosets. You could also do this with other representatives of cosets, but it makes everything more complicated. So this is, whenever I say series representation for a p-adic integer, this is what I mean. Okay, now I want to connect this to the inverse limit, right? And so in order to connect this to the inverse limit, what do? I start with my series, and then I'm going to, I don't know, that should probably be infinity, but I take my series, let's suppose that's infinity right there, and then I look at the truncation of it, right? When I look at the truncation of the series, I can view that as an ordinary integer, right? And it's not hard to see because this is the base p expansion that the value of that is going to be between 0 and p to the l plus 1 minus 1. Right. All right. Well, here's what we're going to do, right? So I'm basically going to use those things right there as elements in my infinite tuple for the inverse limit, right? So I'm basically going to say if I have one of these and I'm going out to j minus 1, right? So one of the truncations going out to j minus 1, I'm going to call phi I of j of that Well, I'm just going to truncate it down to I minus 1. Right? So I'm just going to truncate it further. Right? This is equivalent to reduction modulo p to the I. Right? And these phi ij, it is not hard to see that these things are actually homomorphisms. Clearly, phi ii is the identity. And, well, this is easy to see too, because if I want to truncate from here to here, I can truncate, truncate, and then truncate again. Right? So the connection of the homomorphisms is fairly straightforward. Right? All right, so basically the truncations of the canonical series representation for a p-adic integer is also equal to the inverse limit definition, or can be seen to be isomorphic is what I should say. Okay, series cosets and balls, right? So the question might be, how do we represent balls in ZP now using series expansions? Well, this is not too hard to see. One thing to see is that if I look at p z to the p, right, I'm essentially multiplying everything by z to the p by p, right? That means that the constant coefficient is not constant anymore. It's multiplied by p, and so our sum actually starts at 1. And so PZP consists of all series with constant term equal to 0. Right, that's easy to see. The cosets of PZP, that is the other balls of radius 1 over p, right? They consist of series whose constant coefficient is equal to one of the other representatives. All right, but this correspondence continues. Two series x and y are in the same ball of radius p to the L if and only if their Lth projections are equal, right? These truncations, right, are equal, right? So put another way, x and y are in the same ball of radius p to the L if their series representations agree up to at least the p to the Lth term. In this situation, right, I can look at the ball of radius x, or of radius p to the minus n around x, right? The truncation at L is going to be an honest to God integer. And so I can write my ball as that integer plus this ideal right here. And so this is a way of expressing balls in terms of canonical representatives. Notice one thing that's really nice about this is that this gives us a way of enumerating the balls in ZP via the integers, right? Every integer gives you a different ball. Right. You can do the same thing with QP. I'm not going to go too far into this except to say that QP is also the field of fractions of ZP. So one way of thinking about QP is to think of fractions where you have numerators in ZP and denominators in ZP. Well, both of these things have series representatives. And since they have series representatives, you can do series division, essentially, kind of like polynomial long division, but you're doing it with series. And when you do this, you will get a new series out. However, this new series might have some negative terms, right? Might have some negative powers of p showing up. Right? But this is a canonical series representative for an arbitrary element in QP. And so the only difference between a series representative for an element in QP and an element in ZP is that the element in ZP only has positive powers of p. The elements of QP could possibly have negative powers of p showing up in their series representation. However, they can only have finitely many negative powers of p showing up, right? So we definitely start the series at some point. All right, the final thing to say is great. We have these series representatives for p-adic numbers, but we know that the p-adics form a ring, right, or a field if you're looking at QP. How do you do the arithmetic there? Well, thankfully, you can multiply, divide, subtract, add series, formal series, but you can do Cauchy series as well. What we would hope, and what indeed turns out to happen, is that As long as we do the multiplication correctly, keep in mind when you multiply two series, right, you might have to carry the one, as it were, right? As long as you do the multiplication correctly, so that after you do the multiplication, all of the coefficients in the series are in 0 to p minus 1, right, are our canonical representatives. As long as you do that, then the ordinary operations on series, plus, minus, times, divide, give you the arithmetic operations on QP and ZP. All right, so that was our third model of the p-adics. All of them are useful in different contexts, right? It's not, they have different flavors, and sometimes it's useful just to use different definitions. Sometimes when you're doing calculations, it's very useful to use the series way of doing things, because the calculations become very easy or become very common, right? Something that we all know how to do as mathematicians is multiply series. It's something that doesn't seem hard to us. Whereas maybe if you're not an algebraist, thinking about this in terms of inverse limits is a more abstract or complicated way of thinking about it. But maybe you're trying to prove algebraic facts, and that turns out to be more useful. So all these different representations for QP are useful, and it's kind of interesting that there's these various ways of thinking about them, I think. All right, measures on QP. Now we're getting down to brass tacks, right? We're getting close what we want to talk about. QP is a locally compact abelian group. We've talked about those. It has a natural translation invariant measure, Haar measure. Not uniquely determined just yet, but it has one. And this will allow us to do integration. Okay, sigma algebras, blah, blah, blah. This is some stuff that I've already talked about. Here we go. There is a unique translation invariant measure, lambda, on the Borel sigma algebras of QP, normalized such that the compact ball ZP has measure 1. Right? So again, you have a Haar measure. Haar measure just means that the size of sets is invariant under translation by the action of the group. Right? But that's only unique once you specify the measure of a single set that has positive measure. Our favorite subset of QP, I would argue, is ZP. Other people maybe have other favorite subsets, but I would say that ZP is our favorite subset of QP. And since it is clopin, it is compact and open, if we set that to have measure 1, that will uniquely determine the Haar measure, which we call normalized Haar measure. One reason we normalized it like this is because eventually we're going to restrict ourselves to ZP. And when you restrict this measure to ZP, it becomes a probability measure. Right? So I'm going to be able to do probability on ZP with respect to a very natural measure, Haar measure. It's also sometimes just called Lebesgue measure, in analogy with Lebesgue measure on Rn or other spaces. All right, so just a couple properties of Haar measure. One is we've already noted that ZP is a collection of cosets. And as a collection of cosets, it's a disjoint union. Here's the maximal ideal. Here's the first coset, right? And I add the representative, so there's the last coset. And because there are a total of p cosets, and because each coset is a translation of PZP by that representative, right, we can conclude that the measure of any of the cosets, these top order cosets of the maximal ideal, all have measure 1 over p. Well, why? Because the sum of their measures equals 1, and there are p of them. Right? This is a completely general phenomenon. So if I have a smaller ball, right, p to the n ZP, this has radius p to the minus n, right, and then it has a representative. So it is a translation of this smaller ball, right, and the measure of this ball is p to the minus n. And essentially this is because you can look at all of the cosets of p to the minus n ZP, or sorry, p to the n ZP, right, and those form a disjoint union. How many things are in that disjoint union? P to the n, right? Well, then the sum of a bunch of things, p to the n different things that sum up to 1 is going to be 1 over p to the n. Now I should say something. This is actually a deeper fact than it looks on first inspection. And, maybe not huge. Well, no, we will use this. So this Haar measure was designed to do something nice with respect to addition, right? This translation invariant says if you take any set and you translate it, right, add to it, that the measure of the set doesn't change. All right, and that's really almost the only condition that we put on the measure. It has to be a Borel measure. We have to be in a locally compact abelian group. But the defining condition for the measure is that it is translation invariant. That is, it plays very nicely with respect to addition. There's no reason necessarily that this thing should play nicely with respect to multiplication, but it turns out that it does, right? So instead of having an additive translate, right, x plus b, I can have a multiplicative translate. So I have a Borel set, and then I multiply every element in that Borel set by my favorite element x, right? Then in general, that's going to be a new ball that could be kind of a smaller ball, or well, that could change the size of the ball, certainly. But the point is that if I look at the measure of this, how does it change? Well, lambda of this multiplicatively translated ball is equal to the p-adic absolute value of x times the measure of the ball itself, right? So for instance, let's take ZP. ZP is a perfectly lovely ball. Let's take x equals p. PZP, perfectly lovely ball. We know that that's the maximal ideal. This says the measure of the maximal ideal equals the absolute value of p, 1 over p, times the measure of ZP, 1. And so you just return to this statement of the theorem, of this fact right here, right? That the measure of the translation of the maximal ideal is 1 over p. Right? I do want to just expound just a tiny bit on this formula right here. From the viewpoint of number theory, there's a book called Basic Number Theory by Andre Weil, and he actually uses this property of Haar measure. So he starts with the existence and uniqueness of Haar measure, and then uses this property of Haar measure as a starting place to do number theory, right? And this is beautiful because this kind of gives you a way, if you wanted to, if you started with a measure, this kind of gives you a way of trying to define an absolute value from that measure, kind of, right? You might ask for other measures, can something like this happen, right? And it kind of gives you a way of defining absolute values. And then absolute values we know are basically in correspondence with primes, and then you're kind of off to the races. So if you are interested in reading some really abstract number theory, I would recommend the book Basic Number Theory by Andre Weil. One of my good friends in grad school said, the thing about that book is it's poorly named because it's neither basic nor number theory. And that is kind of true. But at any rate, check it out. Okay, well, I'll just talk about this very quickly. Something like this will come up a little bit later. But QP cross, right? So the set of things in QP, which you can divide by, so essentially everything but 0, is a locally compact abelian group under multiplication. Right? QP is not just a group, it's also a ring. And so if we throw out the 0 element, then the multiplicative structure gives us a group structure with respect to multiplication. And so there's a unique translation invariant measure. There's a Haar measure. We can normalize it by, say, our favorite set in QP might be the set of things that have absolute value 1. So we could normalize that absolute value. And you get an absolute value, which I'm calling lambda cross. And this is the unique multiplicative translation invariant Haar measure if I specify that the measure of the units equals 1. Right. Really, neither here nor there for the purposes of this conversation. However, it is actually really important. Many integrals that you run into turn out not to be integrals over the additive group in the p-adics, but might be integrals with respect to the multiplicative group, right? So, and another thing I should say is, I chose this particular normalization right here, but other people sometimes do different normalizations. John Tate, who was usually right about things, chose to normalize the multiplicative Haar measure so that the measure on UP is equal to P minus 1 over P, because then the measure on that set agrees with the additive measure on that set. Okay. At any rate, just know that there are different choices for normalizations. It's a little bit less canonical. And a fun exercise to do, not hard, but kind of gets you used to multiplicative translation invariance, is to show that if you take the measure of ZP, well, you have to take 0 away, right? But if you take the multiplicative measure of ZP minus 0, the measure of this is actually infinity, right? So different behavior, right? The additive measure of ZP was equal to 1. All right. Geometry of QP and ZP. Now we're going to look at some pictures. So this is going to be kind of the geometric or a geometric way of looking at things. It's not the only geometric way, but it is a geometric way of looking at the p-adics. In this case, P is going to be 5 for these pictures. Okay. So I claim that we can represent Z5 with a shape like this. Okay, so I've labeled some things in here. So 5Z5, that is the maximal ideal, that thing in gray. This is a coset of the maximal ideal. Another coset, another coset, another coset, right? There are other ideals besides the maximal ideal, but they're all products of the maximal ideal. So for instance, another ideal is 25Z5. Right. In this picture, let's see, do I say anything about this? So the 5 adic integers in this picture are the points on the fractal boundary. Right? They're not the line segments. Those were just kind of aid in drawing. And, if you were to keep zooming in, the boundary of this thing is a fractal, and the points in ZP are on that fractal boundary. Right? There are some naturally appearing, I call them pentagons. Right, but really, I mean the fractal boundary contained in a pentagonal region. But every naturally appearing pentagon is a ball, right? So this is a ball of radius 1 over P. This pentagon right here is a ball of radius 1 over 25, 1 over P squared. This littler pentagon right here, right? 1 over 125, 1 over 625, right? Any naturally appearing pentagon, you can assign a measure to it essentially by counting how many other similar pentagons are in the picture, right? So this right here, I count how many similar pentagons are there to this coset. Well, 1, 2, 3, 4, 5. And so therefore, it takes up 1/5 of the measure. If I look at this pentagon right here, 25Z5, I look at how many cosets it has, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 25 of them, obviously. And so since there are 25 cosets of the same size, the size of that is 1 over 25. Right. Similarly, the size of this little guy right here would be 1 over 125, etc. Right. So this is kind of a useful way of writing things down, writing a picture of the p-adics, especially if you are interested in being able to either measure distances, or if you want to compute measures, Haar measure of sets, you can do this schematically, right? So for instance, I know that the distance between 2 points, if I pick 2 points, suppose I pick a point here and suppose I pick a point here, right? So I have a point here and a point here. The distance between those 2 points is equal to the measure of the smallest ball that contains both of the points. Right? So if I have a point here and a point over here, the smallest ball that contains both of those points is this coset, and so the distance between those points is 1 over P. if I have a point, say, in this coset here, and I have a point in this coset here, the smallest ball that contains both of those is the entire shape, is all of ZP. And so therefore the distance between a point in here and a point in here is 1. All right, and this continues. All right. Now, one way we can do is we can describe a point on the boundary of the fractal by systematically labeling the cosets of each closed ball. All right, so by that I mean I've essentially labeled this coset 0, 1, 2, 3, 4. Inside each one of these shapes, right, I could also label the cosets 0, 1, 2, 3, 4. There are other choices. I don't, there's different permutations of ways I can do that, but we're just going to pick one. Right? Given any smaller ball, right, I can label those cosets 0, 1, 2, 3, 4. Right? So I can get a kind of an address for a point on the fractal boundary. Suppose I have a point on the fractal boundary here, right? Well, then the first digit of the address is going to be 3 because it's in this third coset, right? And then the next digit is going to be, well, 0, 1. So then the next, because it's in this coset, right, the next digit is 1. If my point is, say, here, right, then the next digit is also 1. Right? So if I label these nested cosets uniformly in some way, I made a particular choice. It doesn't really matter what choice you choose, as long as you specify it beforehand, right? Then you can kind of write down an address, which is going to be a list of numbers between 0 and 4, right? Each number in the list is going to become between 0 and 4, and that will tell you kind of the turns that you need to take if you were to drive down the path to the edge of the fractal boundary, right? Well, that's neat, because what has that allowed us to do? That has allowed us to represent a number, a p-adic integer, geometrically in this picture with an infinite tuple of integers between 0 and 4, right? Well, we also know that there's an infinite tuple of integers between 0 and 4 when I look at the canonical series representation for a point, right? That's another collection of integers between 0 and 4. And it turns out that is the isomorphism, or the bijection, really, I should say, between this geometric picture and the canonical series representation, right? So if you have a picture like this and you have a canonical series representation, you could drive your car down these little lines until you got to the appropriate point represented by that canonical series representation. Right? So you can actually, if you want, embed points into this picture in a very precise manner if you have the canonical series representation. All right. All right, so as I said, the p-adic distance between two balls is given by the measure of the smallest closed ball containing them. All right, so that is the end of the discussion on the p-adics. Let me go back here because, well, it is 1:51. As promised, that we ended at kind of a nice place. So far, what we've talked about is the basics of probability and the p-adics. The next thing I'm going to talk about today, probably for the rest of the time today, is going to be an introduction to Boltzmann statistics. And then tomorrow we'll get to the p-adic electrostatics. So I'll be back at, how about 2 o'clock my time? So that's about 10 minutes away. And that'll give people a chance to stretch your legs, go get some coffee, maybe escape if you're terminally bored. Whatever you need to do, that is up to you. And I'll see y'all in 10 minutes.
Okay, thank you. So we return in 10 minutes.
Estamos hablando de y sabes que esto va a ser una cuenta. Se pedía una fórmula clara, explícita de la dualidad para límites. Pero porque hay tipo teoría de probabilidad, se acerca, predice que el límite de tomar el igual de un límite de una flechita de vuelta. Solo está que quería, necesito los sí, es que eso es. No, si no funciona bien.
Víctor, ¿vos vas?
Sí, sí, ya sé.
Pero ¿por qué tenés que ir?
Ya.
No, porque capaz pasa mañana. Digo, ¿qué tal si lo hago?
Lisa. Sí, sí, sí. Sí, ya,
Ahí por allá tengo que ver.
la burra.
Sí, por eso yo. ¿Vas solo? No tiene forma de ¿por qué no van a enviar? ¿Van a salir? No les digo.
No sé, no quiero tampoco.
¿Eh?
Quiero tampoco.
Ya, solo no. Cuando yo no, pero la verdad, la tema que yo tiene que darle. No, ahí. Somos un grupo de chicos.
Y en realidad es lo que más.
Es que te recomendaron esto para las próximas para que no se entiende mucho que son. Nos llevan 3 que no tienen español. Y yo solo no tengo español. Eso. ¿Sí?
So, are we ready?
All right. Welcome back, everybody. Hope you had a nice break. It was short, but we're going to talk now. We're going to change gears a little bit and talk about an introduction to Boltzmann statistics, because these provide a framework for the p-adic electrostatics that we're going to be talking about tomorrow. So this is meant to be very general at this point. And so we're back in kind of the setting of some sort of general random experiment. Okay, and this random experiment is going to involve particle models, right? And what we imagine, so physically, the nice thing about this is we'll have some physical intuition and some mathematical tools, but the idea behind the first ensemble that we're going to talk about is that we consider a system of particles where the total energy in the system is fixed. Okay, so an energy function is just some real valued function which is bounded below. Usually the energy function comes from some sort of physical consideration, but mathematically, we can abstract that a little bit. And basically the idea is that if I plug in an element, which now we're calling states as opposed to outcomes, these states describe the composition of the system, that there is some function, energy functional, that will take in a state and spit out a real number that tells you how much energy that state has. In general, motivated by physics, we expect higher energy states to be less likely than lower energy states, right? We can't really talk about that just yet, but in general, right? If a system is allowed to change state or change energy, then we would expect it to want to minimize the energy. That's physical intuition, right? States with the lowest possible energy, if they exist, are called ground states. It turns out that in physics, really, energy, it's not energy which is so important, it's the difference in energy, right? Like when you are computing the potential energy, if you're climbing a hill or something, right? Well, you look at the potential energy that you have at the bottom, and then you climb the hill, and you look at the potential energy that you have at the top, and you subtract those two, right? That's how much energy it took you to get to the top. So it's really the difference of energies which is important in physics. And therefore, you can really, if you want, you can readjust, you can add a constant to your energy functional without changing the physics. So you may as well assume that your energy functional takes non-negative values. Right? The lowest value is called zero energy. Right. At any rate, right. Well, conservation of energy implies that if we have a system of particles and it cannot exchange energy with some other system. So if we have a
Sorry, there is a question here.
Okay, yes, go ahead.
So I agree that you can move the energy, but if you put that it's positive, you're assuming that the energy is bounded by below. Why can't you do that?
Oh, so we're going to assume that the energy is bounded from below. And in the examples that I'm actually going to compute, I'm going to give you an explicit energy functional, right? But that's the assumption. If you have a system that doesn't have an energy functional which is bounded below, well, then it's not going to have a low energy state, and there's not going to be some sort of ground state that you would expect to find the particles in. Right? So it's axiomatic, basically, is what I'm saying.
Thanks.
Yep. Okay, so conservation of energy implies that assuming that we can't exchange energy with another system, well, that the only thing the system can do is transition through states with the same energy, right? So if we believe in conservation of energy, there might be multiple states that have the same energy. But if the system is just going to transition amongst those states with the same energy. All right, the states with a fixed energy are just given by the level sets of the energy functional. Of course, right? And then the fundamental axiom of statistical physics, right, which really we kind of take as a mathematical axiom a lot of times, is that all states with the same energy are equally likely. Right, so this is an axiomatic assumption based on physical laws, but that's going to be an assumption that we're going to make, that if we have multiple states with the same energy, they are equally likely to appear in a system that has that energy. Well, of course, we need to clarify what equally likely means, right? In most common situations, certainly the situation that we're going to be in, the set of states comes equipped with a natural measure. I'm calling it mu here. And so, for instance, if the set of states is described by a subset in Rn, then we have Lebesgue measure that we can talk about, right? And then we can think of the Lebesgue measure of Lu, that's this level set, right? We can call that number Vu. Right, that's the volume of the set of states that has energy U. Okay. Now, if this is a non-zero number and it's finite, right, then the uniform probability measure is just going to be Lebesgue measure, right, normalized by the volume. And then states chosen with respect to that probability measure are said to be equally likely. All right. All right, so finally, more generally, if we're given some other reference measure, right, then we can construct a probability measure on the set of things that have fixed energy U, right? This is going to be our reference measure divided by the volume of that set, and that becomes a probability measure on LU. Right? And then states chosen with respect to that probability measure are said to be equally likely, right? And, you know, quite frankly, we have to have if we have a probability measure, we need a sigma algebra, but we already had a sigma algebra H. And so we can look at the trace of that sigma algebra, basically all the sets in that sigma algebra that live in the smaller set. And that forms a nice sigma algebra on the set of states with energy U. All right. And then the definition of the microcanonical ensemble is just the probability space, right? LU, that's a set of all states with energy U, with this sigma algebra that we've made from H, and then this uniform probability measure on the set of states with energy U. So in general, an ensemble is a kind of probability measure on a physical system. Right? We'll see some more ensembles, but really it's just a kind of a physical language to talk about probabilities that arise in physical systems, just a different word for almost the same thing. Okay, particle models. Here we go. We're getting into the electrostatics that I want to talk about. And we're going to be interested in systems of interacting particles. Right. So in general, the general setup of this kind of problem, there's lots of variations, but a very general setup is one where we have n particles located in some fixed volume V, maybe it's a subset of Euclidean space, equipped with some sort of natural reference measure that will likely be Haar measure, but some natural measure on the set of spaces, and then some sigma algebra. Right. Then in this situation, the set of states can be identified with, well, the n-fold Cartesian product of V, right? Each coordinate telling you where in V a particle is at. The product sigma algebra, right? So we can now talk about, hopefully, what is the probability that we see a particle or particles in a particular set, right? And then a measure. And again, this is usually given in the problem. Oftentimes, the set of states are described in a Euclidean space or some subset there. And so that is usually Haar or Lebesgue measure. And when we move to the p-adics and do this in the p-adics, it will be Haar measure in the p-adics. All right. Now, in some sense, the microcanonical ensemble is a little bit boring, because if what you really want to know is, what is the probability law on states? Where do these particles go? Maybe you want the probability of cylinder sets, right? In general, uniform probability measure is not particularly interesting, right? So in some sense, the only thing that you can really ask about the microcanonical ensemble, once you know the energy that you're at, is what does the level set of that energy look like, right? Can we somehow describe the set of states that has, a particular energy? But there's not really much you can do beyond that, because once you describe them, then the probability of choosing any one is going to be uniform. Right? You don't see some states more likely than others. And so there's not a lot of interesting probability to do in the microcanonical ensemble other than describe the set of states that have a particular energy. However, if we want to do something interesting, and we do, what we want is to allow the energy to vary in some way. Right, so that we are allowed to access states that might have higher energy or lower energy. In order to do this, we will have to deal with the conservation of energy, which we can do. And another way to change the model would be to allow different numbers of particles in the system. Right, so now maybe the number of particles that we're looking at is not fixed. Right, maybe that's a random variable. Okay, so first we're going to talk about the canonical ensemble. The canonical ensemble is the ensemble where you have a fixed number of particles. Capital N is usually what I use to describe those. You do not have fixed energy, but you have fixed temperature. So let me describe this a little bit. What does this mean? Well, in order to not have fixed energy, our system cannot be an isolated system. All right, so we imagine our system being connected to a much larger system that we sometimes call a heat bath or an energy reservoir. Often in physics, a common form of a heat bath would be the rest of the universe, right? Maybe I'm looking at the particles in this little box, right? But the particles on this little box can borrow energy from the rest of the universe. And so the amount of energy in this little box might change as more energetic particles come and go, right? Okay. So in general, this heat bath or this energy reservoir is not really of concern to us. All we care about that at this point is that it can lend energy to our system, or it can take energy from our system. That energy can flow back and forth between the system we care about and this larger system, which is for all intents and purposes to us, not what we're studying, and so is just a structureless reservoir of energy. Okay, now, when you have two systems, and when you take two systems that are initially isolated and you connect them to each other, right, in general, those two systems, energy will flow from one system to the other, right? Maybe they were both at the same energy and you bring them together and nothing happens, but in general, one of them is going to have more energy than the other, right? And so when you bring them together and allow them to start sharing energy, energy is going to flow, right? There is a parameter that kind of controls how easily energy can go back and forth from one system to another, right? And this parameter is temperature. This is a notion of temperature. Probably not how you think about temperature when you're looking at the weather. But nonetheless, temperature is a measurement of kind of how easy it is for two systems to come into equilibrium with each other once they're placed, once they're connected somehow, right? Now, it turns out for various reasons that it's actually more useful to, instead of talking about the temperature, to talk about the inverse temperature. This is a psychological change. If you know the temperature, you know 1 over the temperature. Nothing really changes there. It makes the formulas look a little bit prettier. And so we introduce this constant beta, which is going to be essentially 1 over the temperature. However, temperatures come with units, and since we're mathematicians, generally units ruin everything. And so we need to multiply by this constant K, the Boltzmann constant, which you've probably seen before in the ideal gas law, PV equals NKT. That K and that T are the same K and T that are here. It's just, it makes us a dimensionless number. Okay. All right, so now we're looking at our system. Our system is in contact with a larger system, but still, anytime I say system, I mean ours, the collection of particles that we're looking at, not the rest of the universe. Okay, and now the energy of our system is potentially variable. It can grab energy from the heat bath, right? It could give energy to the heat bath. Energy can go back and forth. The thing that is fixed is the temperature, which basically means that before energy is going back and forth, right, these things have come to equilibrium. I haven't put a really hot thing, and I don't have a really hot thing and a really cold thing. I've put them in contact. They've come to equilibrium at a fixed temperature, and this basically just says how easy it is for energy to go back and forth from our system to the heat bath. Now, we have multiple energies, right? Now we have interesting questions that we can ask. For instance, at this point, our expectation is states with high energy are less likely than states with low energy. All right. Well, so we're going to make a probability measure. Here's how it's going to work. Essentially, I'm going to take my energy functional, whatever that it is, whatever that thing is that gave me the energy of the states. Going to multiply it by beta, 1 over the inverse temperature, and then I'm going to exponentiate that thing, right? That is, something which is dying very quickly as energy goes up. Well, depending on what beta is, but potentially is dying really quickly as beta goes up, right? And in order to make this a probability measure or a probability density, we need to normalize, right? So that when we integrate this over all states omega, we get a probability measure. Right? So basically there is a probability measure such that the density with respect to our reference measure, which is usually Lebesgue or Haar measure, is given by e to the minus inverse temperature times energy, normalized to make a probability measure. The constant necessary to normalize this is called the partition function, and it's exactly what you think it is. It's the thing that you need to normalize this, so it's the total integral over omega of this expression right here. Of course, I'm assuming that this integral is finite and non-zero throughout, right? So I'm assuming that we actually can make a probability measure. If z is either 0 or infinite, then this just doesn't work. Right? So this function is called the partition function. Might sound like a dumb name because it's kind of a constant, a normalization constant, but it is a function of temperature. It's a function of beta. As a matter of fact, it's a function of the number of particles that are in your system as well, right? So it is a function, though sometimes we just denote it as a constant, because here we are essentially treating it like a constant to normalize this. This expression right here, the unnormalized term, e to the minus beta energy, is called the Boltzmann factor, right? And then this is called the density of states, right? The one over is, this is the, basically gives you the density function for the states. All right, so now let's talk about particle models. Okay, if we have n particles and some volume V with some sigma algebra H, right? Maybe it's coming from the cylinder sigma algebra, but at any rate, we have some, some reference, and then some reference measure, Lebesgue measure. Then, well, the state space is basically the n-fold copy of V, basically the tuples that tell us where the particles live, right? We need a more complicated sigma algebra because we have multiple particles. This is just the product sigma algebra, and this is the product measure. This is just basically Lebesgue measure on Vn. Then you can, in this situation right here, you can be a little bit more explicit, and you can write z as an integral over Vn. This right here, depending on what E is and depending on your reference measure, this might be very explicit. This might be something that you can, just a regular integral that you can do if the energy is given to you in an appropriate way and your measure is some standard measure. Now, we've already talked a little bit about this, but in many particle models, the particles are indistinguishable. We cannot detect the difference between one electron and another electron. As far as we know, there are no hidden variables or little labels on these electrons that allow us to say, this electron is named George and this one is Herbert. That doesn't happen. And so in many situations, the particles are indistinguishable. Now, in this situation, we might actually have multiple ways of representing the same state, right? Because the state is the tuple of locations of the particles. But if I can't tell the particles apart, if I permute those locations, I get another state that to me is identical, right? So one way of dealing with this, if you are in an ordered set, or like R or something, is just to put the particles in order, right? And say, well, I'm going to call the first particle the leftmost one, and then the second particle the next one, and so on. So you can put them in order. And then if you put them in order, this is one way of then making the state space unique. Well, almost surely unique, right? There are issues of when you have, say, x1 equals x2, you might have multiple representations still, but it turns out that in general, that's a probability 0 event, and so we can ignore it, right? At any rate, this gives us a way of more uniquifying the representation of our states if we are in an ordered set. More generally, if you're not in an ordered set, right, what you can do is you can say, well, any two permutations of the same vector give me the same state. So essentially, you can take the state space and mod out by the action of the symmetric group on the state space. In principle, that would give you a region kind of like this, except not written down with respect to some ordering. Now, it can be useful, depending on the context, to sometimes, instead of integrating over all of Vn, right, to just integrate over a more unique set of states. Right? And when we do this, we put a little tilde on top. Right? Now, it turns out for the canonical ensemble, it really doesn't matter if you use Z tilde or not. And the reason for this is because basically the only difference between Z tilde and Z is essentially a 1 over n factorial, right? If I hit this with the action of the symmetric group, I will get all of this, right? And so these things basically differ by 1 over n factorial, right? But the probabilities that we care about, if there's an n factorial on the top and the bottom, right? If I put an n factorial in f of x and then I put an n factorial in z tilde, it's going to cancel. So for the canonical ensemble doesn't really care a whole lot whether your particles are indistinguishable or if they're distinguishable. Right? We might care. The events that we might consider might, reflect the fact that we view the particles as indistinguishable, but the canonical ensemble itself says, I don't care if there's an n factorial in the denominator or not. That's going to cancel when I normalize the Boltzmann constant. Okay. Now here is kind of an argument for there are some particles that satisfy the Pauli exclusion principle, fermions, and fermions can't be located at the same point in space at the same time, right? And so in that situation, you'll never observe a state where you have two equal particles, or that's a probability 0 event, right? In which case, when you look at this principal chamber right here, you wouldn't have less than or equal, you would just have less than there. At any rate, neither here nor there, except that sometimes there's a physical reason which allows you to completely uniqueify your description of states. All right, so a little bit of notation. Things get a little bit hairy because we're dealing with multiple ensembles. We have various parameters as well, right? We have beta as a parameter, that's inverse temperature. We have the number of particles, right? We might want to talk about 10 particles or 1,000 particles. We have a volume that these things are contained in. There might be other parameters to the system, right, that restrict it in some way. And so since the partition function in general is a function of these things, sometimes it's useful to explicitly denote the functional dependence, right? And there's various ways of doing this, depending on how large or small I want the equation to look. Sometimes if all I care about is n, I'll write Zn. Maybe I care about Zn of beta, but the volume is understood, etc. But the idea is that Z will always be a partition function, and the variables that I put in it kind of tell you parameters of the system that you may want to vary, right? Perhaps to make a new system or not. Similarly, there's other quantities that depend on various things, and so the density of states we might subscript with an n or write an n and a beta if that's important, right? This becomes important later, or at least hopefully this will allow us to clarify, because we're going to see another kind of partition function here in a second. All right, so canonical ensemble. So let me just review real quick. Microcanonical ensemble, a bunch of particles stuck in a system at fixed energy. Pretty much all you can do is describe the possible states that the particles can be in, right, at that energy. Canonical ensemble. Canonical ensemble, energy can vary, temperature is fixed, right? So now we can access higher energy levels or lower energy levels, right? There's some variability in energy, but as we see from Boltzmann's factor, the larger the energy is, the smaller the probability is, right? And this kind of makes sense. Now there is this beta, right? There's this e to the minus beta energy, right? If beta equals 0, right? That's infinite temperature. And so the energy doesn't come into play at all. And that's because the temperature is so high that the particles just have all this thermal energy, and the thermal energy far outweighs any sort of, say, electrostatic energy or some other reason that these particles might want to stay away from each other. When you are at infinite temperature or beta equals 0, you know, the energy becomes unimportant because these things are just going all over the place. Right. The other interesting value of beta is beta equals infinity. At beta equals infinity, this is at absolute 0, right? And it turns out that all at beta equals infinity at absolute 0, all of the particles want to be in the lowest energy configuration, and they can't get out of the ground state. So really, in that case, you kind of reduce yourself to the microcanonical ensemble in the ground state, right? And that's because these things are essentially frozen in place. All right. So the next thing we're going to talk about is the grand canonical ensemble. So in the grand canonical ensemble, we have our system as we did before, our canonical ensemble. The energy can vary, the temperature is fixed. Now, the number of particles can change. In the canonical ensemble, you are always dealing with some fixed number of particles that you describe. You have particles in a box, and that's all the particles that there are. In the grand canonical ensemble, we have our heat bath, or the rest of the universe, and now our system over here can borrow not only energy from the heat bath, but it can borrow particles, or it can give particles up. So particles can go back and forth between our system and our heat bath. All right. So when we do this, right, is there a question? No, okay. So when we do this, remember we had to introduce this parameter beta, which basically kind of told us how easily energy can go back and forth between the heat bath and our system, right? Similarly, there is another parameter called the chemical potential, which tells us how easily we can exchange particles with the heat bath, right? How easy is it for me to grab another particle or give a particle up? You can kind of think of the chemical potential as maybe being a cost per particle, right? Or maybe it's set up that when you have more particles, right, you actually, you know, lower your energy or something, right? It doesn't have to be a positive cost per particle, but you can think of the chemical potential as kind of being how easily the system exchanges a particle with the heat bath. And you know, in some sense, it is a discrete version of the inverse temperature, right? Temperature is continuous, and so you have this continuous parameter that tells you, you know, how easy it is to switch that for energy to go back and forth. Likewise, there is a parameter that tells us how easy for particles to go back and forth. There are other ways to use the chemical potential, I should say. For instance, maybe you're dealing with a model where you have, you know, two different kinds of particles in the system, and maybe, you know, maybe these two kinds of particles want to sometimes form a bond and form some sort of molecule, right? Then the chemical potential is basically going to be how easy is it for these two particles to come together and replace these two individual particles with one molecule. Right. So this is where the name chemical potential comes from. It tells you how easy it is for a chemical reaction to occur, generally in real life, but we're using it mathematically here. Now, before, in the canonical ensemble, we had a state space, right, which allowed us to describe the locations of n particles. Let's call this omega sub n. The number of particles is important here. And so now our new state space in the grand canonical ensemble is the disjoint union of all those omega n's, right? If I have 5 particles, I'm an omega 5. If I have 8 particles, I'm an omega 8. It is possible that I could be in either one of those things. So my sample space, my state space, has to allow me to describe configurations with an arbitrary number of particles, right? But the system can only have one number of particles at a time. And so this is a disjoint union. Okay. So what we want to do is we suppose that we have some energy functional. We'll get down to some brass tacks and talk about some specific ones here in a minute. But the way we change the energy functional in the grand canonical case is essentially if we are in a state with n particles, we use the energy associated to the n particles. But now here is my cost per particle. Each particle n increases the energy by chi, right? And again, chi could be negative here. The sign is kind of arbitrary, and it depends on if you want your system to be accepting more particles or not as to whether chi is positive or negative. But at any rate, we're thinking of this as being the energy between the particles in the system, and then the energy contributed by just having the particles in the system, not due to interactions. Right. Well, Boltzmann's equation is still valid. And basically, the Boltzmann factor says that energies are exponentially disfavored. High energies are exponentially disfavored. Okay, so we still have a Boltzmann factor that's going to look like e to the minus beta times the energy functional. When we do that, right, we're going to get basically, we get an e to the minus beta chi that also shows up right here. Right? Basically, exponentiating this gives us the same Boltzmann factor as before, at least on the set with n particles. But then we have this additional term, e to the minus beta chi. Okay. All right. So if I have the joint probability density of particles in the canonical ensemble, so suppose I know that once I have n particles, right, and then I know from the canonical ensemble, this is their distribution based on Boltzmann statistics. Then we can come up with a joint probability density of particles in the grand canonical ensemble. Right. Here's what you have to do, though, is because this is a disjoint union, right? The best way to describe any distribution on this disjoint union is going to be a conditional distribution based on the number of particles, right? So the way I'm going to describe the distribution is say, well, the conditional distribution for 100 particles is blah. The conditional distribution for 150 particles is blah, right? I tell you the conditional distribution for each of the number of particles, right? And from that, you can compute probabilities. Well, how? You would compute the probability that you have that many particles, which we'll see how to do. And then you will multiply times the probability of whatever configuration of particles you are trying to see. Right? And so we actually describe a probability measure on omega by saying, if I know that A is an event corresponding to having n particles, so I'm kind of conditioning on having n particles, then the probability of seeing that event, right, is going to be the probability from the canonical ensemble, right? This is from the canonical ensemble, times, remember, this probability from the canonical ensemble is normalized by the canonical partition function, right? We don't want that. We want it normalized by a different partition function. So we multiply the z and beta to cancel that thing right there. And then we put in the grand canonical partition function. And the grand canonical partition function is the integral over all states of e to the minus beta times the energy. Okay, but now that integral is over this disjoint union. So if you have an integral over a disjoint union, you have a sum of integrals, right? So here is the sum of integrals corresponding to the disjoint union. I have exponentiated the energy functional, right? That has given me an e to the minus beta chi. There should be an n right there, right? The minus beta chi n. I am using the n factorial here because I'm assuming my particles are indistinguishable. And now it's important that I use the n factorial because it's not just going to cancel away, right? It's not going to show up in the numerator and the denominator. And then I'm integrating over omega n, just the e to the minus beta, the Boltzmann factor, right? So this is the grand canonical partition function. It looks like a bit of a mess, but let me say just a few things about it. First of all of these integrals in here, up to a normalization constant, if you can figure out the probabilities, the partition functions in the canonical ensemble, then you will have those parts figured out, right? So if you can solve for the partition function in the canonical ensemble in some way, the rest of this is fairly straightforward. E to the minus beta chi n over n factorial, right? You are in a relatively simple situation. One thing to note is that the probability of seeing n particles in the grand canonical ensemble is just the ratio of the canonical partition function for n divided by the grand canonical. And that basically just follows from this expression right here. Now, there's one thing I want to do. This is going to take us a little bit away from physics and a little bit more towards mathematics, but it's something that we can reverse at any time we want if we have some physical question we want to answer about the system. What I'm going to do is I'm just going to I'm going to redefine or just define a variable lowercase t, and I'm going to call it e to the minus beta chi. Right? So this basically is a function of beta and chi, but I'm just going to call it t. And really, since this should be e to the minus beta chi n, when I substituted n, what I see is that the grand canonical partition function is equal to t to the n over n factorial times the canonical partition function. That is, if I view things like this, the grand canonical partition function is the generating function for the canonical partition function, the exponential generating function, right? And that can be useful in various contexts because oftentimes, if you understand the generating function well enough, you can use tricks from analysis, differentiating and plugging in 0, for instance, in order to pull off the coefficients, right? And so this direction says that if you have enough information about the canonical ensemble, you can learn about the grand canonical ensemble. And this direction says if you know enough information about the grand canonical ensemble, you can peel off information about the canonical ensemble, right? And so it's useful to sometimes set this substitution, right? So we see this more clearly as a generating function. Right, but this hides the fact that T is really dependent on the temperature and the chemical potential. So there's some reasons that one might not want to do this because you lose a little bit of physical intuition by moving to this kind of nondescript parameter T. Nonetheless, this parameter is sometimes called the fugacity of the system, which is a pretty cool name if you ask me. There used to be this punk band in the 90s called Fugazi. That's what I think about every time I think of fugacity. Neither here nor there. Okay. Next, two-dimensional electrostatics. We're getting really close to p-adic electrostatics, but we're going to talk about more classic two-dimensional electrostatics because this is going to be the analogy that we are going to pursue in the p-adic case. In two-dimensional electrostatics, what we really imagine is that we have infinite parallel lines. Think of them as being wires. And these wires have some charge density, right? So imagine just a bunch of parallel wires with charge densities, right? I can take these wires, since they're all parallel, I can insert a plane which is perpendicular to all of them, right? And then I can look at the intersection of those lines and the plane. And so I can identify the location of these wires with points on the plane, right? I'm going to call these points on the plane. I'm still going to call them particles right? In order for this physics to agree with kind of classic Coulomb electrostatics, you have to view them as these wires. But I'm just going to pretend that we're stuck in the complex plane for all intents and purposes, but some plane, right? And that I have particles at some set of locations in the plane. And really what these are representing is infinitely long wires sticking perpendicular out of that plane. Okay. Well, one can actually just write down, one can just do the physics in this case. Basically, we know the inverse square law between any two particles, and therefore we know the potential between any two particles. And if I have these long lines of charges, right, I can kind of break those lines up into little chunks. Each chunk kind of acts like its own charge, and you can kind of do an integral, and you can just derive the energy functional from the inverse square law for electric charges in this situation. And because these things are infinitely long wires, you get a different sort of potential than you did with just particles. And it turns out that the energy functional in this case is given by, you take the particle locations, okay, so they're located at Z1 through Zn, right? Each two particles, say Z1 and Z2, suppose Z1 has charge Q1, Z2 has charge Q2, then the potential energy of that system is going to be the product of those charges times the log of the distance between them. It really, that should be negative, right? Because what you want is let me think about this. Log of 1 equals 0. Yeah, okay. Right, so if I want the general energy functional, if I have a bunch of particles, right, if each one has unit charge, so Q1 equals Q2, then I sum over all pairs of particles, and I take minus the log of the distance between those particles. So this is the sum of the pairwise interaction energies between all pairs of particles. And this is also based on kind of another axiom of physics, which is that if you have kind of a system made up of a bunch of smaller systems, right, that are interacting, then the total interaction energy is going to be the sum of the pairwise interaction energies. There are places where this is violated, but that's a common thing to do, is to say, oh, well, you just need to look at how the particles themselves are repelling each other, and then you sum up all those interactions. Uh-oh. Oh. Okay, I'm going to try again.
So you may need to reconnect.
Okay, can you see now? Can you see my screen now?
Yes, that's good.
Okay, apologies for that. Okay, now this is a beautiful formula, because the Boltzmann factor is the exponential, essentially, of the energy. Right? There's an inverse temperature in there, but if the energy is given in terms of logarithms, exponentiating does good things to it. Right? So in particular, if I exponentiate this thing, the sum turns into a product. Right? And so the Boltzmann factor is, well, there's a partition function in the denominator. But the Boltzmann factor is just the product of the distances between the particles raised to the beta. And then the partition function is the integral of that over the plane, right? Or over the, say all of the particles are in Z, so over Cn. And so we get an integral that looks like this, right? This is beautiful. Now, one thing to notice about this is that this is the probability density. And if any of the two particles are equal, if Zn equals Zm for some n not equal to m, then the density is 0. What that says that almost surely you will not see two particles on top of each other. Cool. But it's more than that, because this thing right here is a continuous function, right? There's nothing discontinuous about this function, at least on the space we're talking about right here. And so as the particles get close to each other, the Boltzmann factor is small. And that's because as particles get close to each other, the energy is going through the roof, right? These particles hate each other. They have the same charge. And so the particles don't want to be close to each other, right? And so what we see is a kind of repulsion. This is like a probabilistic kind of repulsion because the probability density is small when two particles are close together and is equal to 0 when those particles are on top of each other. Okay. All right. Now, oftentimes when you're working in the situation in the Euclidean space, right, or CN or something, really, sometimes what you need to do is not, how do I want to put it? We've put a bunch of particles into the plane. These particles all hate each other, right? They're all charged and they all want to get away from each other. If we allow them to roam free in the plane, the way that they're going to minimize their energy is they're all going to run off to infinity, right? They're going to try to get as far away from each other as possible. This is a completely uninteresting system. And so sometimes what we need to do is either look at those particles in some subset of the plane, lock them in a box, as it were. That way they can't get too far away from each other, or otherwise introduce some other kind of potential in the system that basically says, well, you know, there's a gravity well, or there's some other thing that is pulling the particles to the center of the picture so that they don't all run away. Right? Oftentimes we do that with what's called a weight function, right? But really you can encode that with just some other measure mu, right? So this measure mu could be based on lambda. Maybe this is the measure that's just, you know, on a box or something. Okay. Now, the last thing I want to talk about, and I'm going to talk about this very quickly because it's not really applicable, and then I'll be able to wrap up so that I don't hold you too long today. The reason I say it's not applicable because the tools that come up here just don't apply in the p-adic case. However, this is kind of where I cut my teeth, and I want to just show you just one really pretty calculation. Okay, if I have a bunch of variables, z1 through zn, right? You've probably seen this before. I can make this matrix, which basically has powers of z, right, of all of the z's, and I make a square matrix. This is called the van der Moon matrix, and the determinant of the van der Moon matrix is the product of the differences of the z's, right, in a particular order. But right, this is easy to see. I'll let you prove it. So here's a theorem that if I am in the canonical ensemble when beta equals 2, right? So I have some partition function here. This partition function can be written as the determinant, and the entries in the determinant are inner products of the polynomials, well, with respect to the measure mu, right? So basically, you can form L2 of the measure space. L2 of a measure space has an inner product. That inner product looks like this. And so this is a matrix of inner products. Well, a matrix of inner products is called a Graham matrix. But let me just show you one quick trick, and then I will leave y'all for the next session until tomorrow. But it turns out that if I pick any family of polynomials such that the degree of the polynomial is correct, right? So the degree of P0 is 0, the degree of P1 is 1, etc. If these are monic, and I form the determinant of the matrix formed from not applying Z1 to the monomials like I did here, but I plug Z1 into all of my polynomials in the list, make a column, plug Z2 into all my polynomials in the list, make a column, and I keep doing this to make a square matrix, then it's not hard to see that the determinant doesn't actually change. Right? And I can talk you through that, but the determinant, that gives you a different kind of van der Moon matrix, but the determinant of that matrix is equal to the determinant of the van der Moon. Okay. And then the thing that I wanted to show you, the last thing I'll say today, is that if you choose your polynomials to be orthogonal with respect to that measure, so that is that these polynomials, if I take two of them with different indices and form the inner product, is equal to 0. So if I have orthogonal polynomials, then you can write the partition function when beta equals 2 just as the product of these would be norms in L2, but of the inner products of the polynomials, the orthogonal polynomials with themselves. Right. And so this is an example of solvability of the partition function. This is the beginning of the story, not the end. But in this case of two-dimensional electrostatics in the complex plane, you have very powerful algebraic tools, the van der Moon determinant, which allow you to actually explicitly evaluate the partition functions. And it turns out that that will then tell you something about the probabilities. All right. I'm going to wrap up right there today. I've basically gotten through all of the background material I wanted to get to so that we can talk about the p-adic electrostatic situation. So tomorrow I'll pick up, and what we're going to study is the canonical and grand canonical ensembles when we put a bunch of particles into ZP, the p-adic integers. All right. Thank you, everybody.
Okay, you're welcome. There's any question? Yes.
Hi.
Hello.
So the reason that you cannot do this in QP is basically because you don't have conjugation, right? Because using conjugation, you have an inner product and you can do what you did there. Is that correct?
Well, so the reason that you can't use this trick in ZP is because in this case, what we had was the absolute value of the van der Moon determinant squared, right? And so I can evaluate the complex absolute value of the van der Moon determinant squared. I can multiply that out and write that as the determinant of the van der Moon times the determinant of the complex conjugate of the van der Moon. And so I can essentially get rid of that absolute value just by multiplying by one version and a conjugate version. Now, you can't do that in the p-adics. There's nothing that, if you're looking at the absolute value of a van der Moon determinant, a p-adic absolute value of a van der Moon determinant, there's not some constant that you can find to get rid of that absolute value. There's just the p-adic absolute value is just so different from either the real absolute value or the complex absolute value that you can't ever get the van der Moon determinant outside of the absolute value in any sort of reasonable way. So we have to use just completely different tools than we can use in random matrix theory.
Thank you.
Another question?
Okay.
Anyone else? So, okay, I guess no more questions.
Oh, there's one.
So yes, Mohammed Reza is having a question. So please, Mohammed.
I wanted to ask if there is any interpretation for n goes to infinity of the partition function, or
so. Yeah, the answer is yes, and I think the right person to talk to is probably Wilson or Edwin. There is the notion of a thermodynamic limit where you're sending n to infinity in such a way that the free energy per particle goes to a constant. Yes, there is a theory there. Most of what I'm going to be talking about will be either in the canonical case where we have fixed n and talking about probabilities of cylinder sets, or in the grand canonical ensemble where n can vary, so it can be quite large, but it's in some distribution. But yes, there is a theory of what happens in the thermodynamic limit, and I would refer you to Wilson. Probably has the best idea of where to read up on the details there.
Just a quick comment. You can see the paper recently published in the Journal of Mathematical Physics. Chris already mentioned this, already showed this reference at the beginning of his talk.
That's right. yeah, it has graphs in the title somewhere, and Coulomb. It's a very nice paper, and I would suggest, yeah, look there, because it has different tools than I use.
Okay,
Thank you.
so anyone else? No? So thank you very much to the speaker.
Thank you, everybody.
So
And
see you tomorrow.
see you tomorrow.
And
Thank
then
you.
Okay, bye. So we resume in half an hour.
30 minutes. Estas son las que mencioné. Claro, porque el sitio trabajo. Sí, sí. the last lecture of the day.
So we are about to start the last section of the day. So we have Angela Rocio Fuken-Tibata that is going to talk about periodic endpoint open strings amplitudes. Thank you.
Okay, thank you so much. Thank you to the professors by organizing this event. And thank you to you for being here. Today I'm going to talk to you about periodic endpoint open string amplitudes. And this talk will be, let's stop. That doesn't work. Some technical problems. Okay, this talk is divided in two parts. The first part is will be done quickly because you are expert in periodic analysis. And then the second part is about periodic open string amplitudes. Okay. String theory is the theory of tiny one-dimensional extended objects propagating in underlying Riemannian or pseudo-Riemannian space-time manifold M. The string theory was motivated by a need to understanding certain aspects of the strong interactions of elementary particles. These interactions are described by scattering amplitudes, which satisfy some general physical requirements. In general, give a formula for the scattering amplitudes is not too easy. The first formula that was done was given by Veneziano in 1068.
1968.
I'm sorry. Yes, 1968. I'm sorry. I'm sorry. It's a typo. In 1968, I'm sorry, Veneziano proposed the following function for describing the interaction of both particles. Here, alpha is this function, linear function, and S and T are given by these formulas. K1, K2, and K3 are the momentum of the particles. And then these amplitudes was generalized to the case of n particles in this way. So these amplitudes can be generalized in for n particles, taking this formula. This is known as Covan-Nielsen amplitudes. Here, K1 to the Kn are the momentum of the particles. In the periodic case, the periodic string theory started around 1997 with the work of Bolovich, Freud and Witten, and Frampton and Okada. I don't know if it's the correct pronunciation. Bolovich noted that the integral expression for the Veneziano amplitude of the open bosonic string can be generalized to the periodic integral and to an algebraic integral. The periodic string amplitudes for m particles have this form, where capital K is a vector, and each entry is again a vector in the space R2L+1. In general, this amplitude can be generalized to over other local field, in this case QP. Okay, one important thing is that there is not a rigorous mathematical way to obtain this formula, starting to the general definition of the amplitudes. So this talk is based in this paper, Euclidean quantum field formulation of periodic open string amplitudes. Its paper was published, was recently published, and is online, free access. If you want to read, please feel free to do that. And in this paper, we study in a rigorous mathematical way periodic quantum field theories whose endpoint amplitudes are the expectation of products of vertex operators. We show that this type of amplitudes admits a series expansion, and in the lowest term, we obtain the periodic open Covariant string amplitude. Okay, and quickly overview in periodic analysis. Remember that the field of periodic numbers is the completion of the field, the rational field Q with this norm, and we can extend this norm to the case in a dimensional case, taking the maximum of the entrance in the vector, in one vector in QPN, in this form, and QPN becomes an ultrametric space. Remember that we denote in this form the ball with center in A and radius P to the R, and the sphere is denoted by this one. And as a consequence of the ultrametricity, balls and spheres are both open and closed subset in QPN. And the topological space QPN with this norm is a totally disconnected space. Some notation, we denote omega, capital omega, the characteristic function of the interval 0 to 1. And remember that we have this notation, capital delta, for the characteristic function of the balls with center in 0 and radius P to the K. And in the lower case, delta K is equal to P to the NK times the characteristic function of the ball with center in 0 and radius P to the minus K. Okay. We consider functions given from QPN to the complex or real set. And we say that this function is a locally constant function if for any x in QPN there exists an integer L depending on x such that the function is constant in neighborhood of x. If in addition this function has a compact support, we say that this is a test function or Broussard-Schwarz function. Remember that we denote this space with this D. In the real case, we are going to denote dr, the space. The set of the continuous linear functionals in the test function is denoted by the D prime. This is called the Broussard-Schwarz space of distribution. We endow this space with the weak topology, and we are defined in one map in the product of not in the product with the distribution and the test function given by the evaluation. This is now as the pairing is a bilinear form which is continuous in each entrance. For rho, belonging in this interval, we denote L rho, the space of complex valued and Borel measurable functions G satisfying this condition. We can give a norm in this space. This norm is given by this, and it becomes a Banach space. If we have an integrable function, we define the Fourier transform of this function in this way. In this case, this is an additive character. The nx is the normalized Haar measure on QPN. And one thing when we are working with a test function is that we don't have a definition for differential. So we need to work with other operators. One of these are pseudo-differential operators. One of these is the Vladimir operator. This operator is defined in the test function and goes to the L2. Is defined by this expression. Sometimes it's called the analog to the derivative in first derivative in the real case. Okay, this operator can be rewritten in this form as a convolution of a generalized function with the test function. In this case, this function is called the Ries kernel. Here appears the periodic gamma function that is defined in this way. Okay, one different thing with the real case is that the test functions are not invariant under the action of the Vladimir operator. So if we need a space invariant under this operator, we need to change the space. So we define the Lysorkin spaces of second kind. The Lysorkin spaces of second kind is denoted by L and is the set of all test functions that have average 0. And in the real case, we are going to denote LR, and L prime is the topological dual of this space, and it's called the periodic Lysorkin space of distribution of the second kind. Okay, as I said, this space is invariant. We define the inverse of the Vladimir operator in these spaces, and the inverse is given by this formula. Notice that because theta is in the Lysorkin space of second kind, the Fourier transform evaluated in 0 is equal to 0, so this is a Lysorkin function. Okay, we are going to start with some of the paper. For do that, we need some notation. We denote capital K, the vector, such that each entrance is again a vector in Rd and is known as the momentum of tachyon. We fix the dimension of our space, and we take D to denote the dimension. Sorry, and the phi is a vectorial function such that each entrance is a test function. We take the notation A dot B to refer the standard scalar product in Rg. Okay. The naive Euclidean version of the periodic endpoints amplitudes is given by this formula. In this formula, zeta 0 is a normalization constant. S is known as the action over the fields. The analog to the real case is to take this action to this part. And these are known as vertex operator. In this case, we are working with tachyons. So the general formula for the vertex operator are this is a product of vertex operator, and this is a measure over the fields. Most of the case, the calculus are very formal in physical sense. We don't have shown the existence of this measure. So the idea in the paper was to show that exists a measure in the fields and to try to construct the amplitudes. Okay. Notice that the action can be rewritten in this way. This is important because if we rewrite in this way, appear the Vladimir operator in the action, so it will be used to define the measure. The first thing that we need to do is then to show the existence of this measure. So to do that, we show the existence the measure in the dual space, and then we take the restriction to this measure in the space of functions. One form to construct measures in the dual space are using Gaussian measures, and to construct this measure we need a particular requirement in the space of functions. The property that we need to have the fields that the space is a nuclear space. Okay, I'm going to construct the measure. We define the bilinear form B in this space in this way. This is the product in L2, and it's the product in L2 between the first component and the inverse of the Vladimir operator evaluated in the second component. We can show that this bilinear form is positive and continuous. And I say that we need to work in a nuclear space. In this case, we have that the Lysorkin space of second class is a nuclear space, and now that this space is dense and continuously embedded in L2, and we have this Gelfand triple. L is embedded in L2 and is embedded in L prime. And we are working, we need a measure, so we need a sigma algebra. We work with the sigma algebra generated by the cylinder subsets in the dual space. Okay, we define this, we consider this mapping, defining in the Lysorkin space the real space given by this expression. We can show that this is a characteristic functional. It means C evaluated in 0 is equal to 1. It's positively defined and is continuous. So there is an important theorem called Wagner-Milnow's theorem that says that if we have a characteristic functional, there exists a unique probability measure P in the dual space with the cylindric subset as a sigma algebra, such that this characteristic functional is the Fourier transform of this measure. So if we have this characteristic function, we have one measure. And I'm going to go back. Remember that here we need to define a measure in the space of fields. And remember that these phi are vectorial functions. We have a measure only in one entrance. So we are working with the product. Okay, with the node PD, the product of these measures, and we are working with the product sigma algebra and this product space. Okay, intuitively, the endpoint amplitudes are expectation values of the product of vertex operators with respect to the measure in the fields. In this case, our measure is PD, so we need to calculate the expectation value in this measure, and it's this definition. One thing is that we are working with locally constant functions, so this integral is a divergent integral. So we need to take a cutoff. We define ARN in this way. So we restrict this integral only in the ball with centering 0 and reduce p to the r. And that we take as a definition is this one. For a positive integer r, we define the periodic endpoints amplitudes as this limit, where this part is given by this expression. Okay, notice that we have changed the integral. The usual form is in this one, and we have the other one. But we show that ARN is finite for any k, and furthermore that we can change the order of the integration. So it's a good definition. Okay. There are some technical calculation that I didn't put here because it's very long, but with some calculus, we can write this ARN in this form. Okay? Other thing that, or other requirement that needs the amplitudes is that they need to be invariant under Mobius transformation. So, because the amplitudes holds this condition, we can fix 3 points. We fix x1 equal to 0, xn minus 1 equal to 1, and xn equal to infinity. And this point for convention means that the endpoints amplitude do not depend to the xn. And taking this condition, we write our ARN in this form. Okay. Okay. Other thing that we can do is to use the Taylor expansion for the exponential, so we can write ARN in this form. Okay. Notice that. Okay, I'm going to introduce a new notation. I call this first part in one form and the second part, and the integrals in the second part in other form, in this form. So I take ARN. This is the first part in the last expression, and these are the integrals inside the second part in the last expression. Notice that the first one is a local theta function. And in the second one, if this product is a test function, we have a local zeta function too. And there is a paper given by Professor Zuniga, Professor Miriam Bocardo, and Professor Compean that where they shows that the Covan-Nielsen amplitude can be obtained as a regularization of local zeta function, and they shown that this expression is can be regularized when R goes to infinity using local zeta functions. So using this result, we have that this the first part in the sum can be obtained as a regularization of a zeta function. This is the Covan-Nielsen local zeta function. If you remember in the notes, this is this expression, and they obtain that this is holomorphic function in certain domains C to D naught. So we can conclude that this limit exists for K belonging in a non-empty subset of C to the D naught. And in the other case, we may assume that this is a test function, then this expression are multivariate local zeta function, and in the same case can be seen as regularization of local zeta function, and we have this bond for these expressions. So note that this expression depends on the Covan-Nielsen local zeta function. Then, because this one converges in a non-empty open set, we conclude that this one converges in the open set where this one converges. So we have the mean theorem in the paper that is this one. The amplitudes satisfy the following for R fixed. We can split this as a series, and the first part converges when R goes to infinity, and can be obtained as a regularization of a Covan-Nielsen local zeta function. And in the second part, we have a series when each term is a multivariate Igusa local zeta function, and each term here converging in a common non-empty open set. Two open problems for now is that we don't have the convergence of all the series. We have that each term converges, but I don't know. We don't know if all the series is a convergent series. And other thing that we need to study is which what's is going on when R is going to infinity in this part. In this one, we obtain then the periodic Covan-Nielsen open string amplitude in a lower level. And it was fast. Thank you.
Good. Thank you very much. So any question or comment? No? So not in the chat. So thank you very much, Angela.
Okay, guys, see you tomorrow. Yeah, fantastic.
Okay, so thank you very much, everybody. That's it for today. See you tomorrow morning, 9:30.
Ahora pueden ir a festejar. Pueden ir a celebrar.